Picture a sky where not one, but 10 blazing stars hang overhead, their light weaving in a complex, eternal dance. Imagine the shifting shadows, the kaleidoscope of colors, the sheer, overwhelming presence of multiple suns governing the heavens. This isn't science fiction, it's the reality of Decuple star systems, cosmic configurations so complex and rare they push the very limits of what we thought possible. For centuries, we looked up at our single, familiar sun and built our understanding of the universe around it. But out there in the dark, these stellar families defy every expectation, creating gravitational ballets and celestial environments that are as bizarre as they are beautiful. They are the ultimate expression of cosmic chaos and order intertwined, and the discoveries scientists are making about them are rewriting the textbooks of astronomy. Welcome to a journey into the heart of these extraordinary systems. Today, we're diving deep into 30 of the strangest, most mind-bending finds researchers have uncovered. We're talking about planets with multiple shadows, orbits so tangled they look like a ball of yarn thrown into space, and gravitational forces so intense they twist space-time itself. This is the ultimate celestial party, a gathering of stellar giants where the rules of physics are not just bent, but completely reinvented. From worlds that might experience perpetual daylight to stars that steal material from one another in a cosmic tug-of-war, each discovery peels back another layer of the profound mystery surrounding Decuple star systems. It's a topic filled with wonder, with "how is that even possible?" moments waiting around every corner. This exploration is about more than just cataloging bizarre facts. It's a window into the incredible creativity of the universe. It challenges our place in the cosmos and expands our imagination about what kinds of worlds and phenomena could exist. By understanding these extreme environments, we learn not just about distant suns, but about the fundamental forces that shape all of reality. So get comfortable and open your mind to the possibilities, because what you're about to discover will change the way you see the night sky forever. The journey into the strange and spectacular world of Decuple star systems starts right now. The journey into this strange stellar reality truly began with a discovery that sent ripples through the entire field of astronomy. For a long time, the idea of a 10-star system was considered almost a fantasy, a theoretical curiosity that was unlikely to actually exist in the chaos of cosmic formation. Then astronomers found it, the first confirmed Decuple system, a complex family of stars bound by gravity, was identified and given the rather unpoetic but precise designation of OBCDEFGHIJ, a string of letters reflecting its staggering complexity. Nestled within a dense star-forming region, this system wasn't found by looking at a single snapshot in time. Unraveling its secrets required years of patient observation, combining data from powerful ground-based telescopes and sophisticated space observatories. The methods used to piece this puzzle together are a testament to human ingenuity. Astronomers relied heavily on the radial velocity technique, which involves watching for the subtle wobble of a star. As stars in a system orbit one another, they tug each other back and forth, causing tiny shifts in the color of their light due to the Doppler effect. Imagine listening to a siren on a passing car. The pitch changes as it moves toward you and then away. Astronomers do the same thing with starlight. In a system this crowded, the wobbles are not simple back and forth motions but a chaotic jumble of gravitational pulls, creating a data signal that looked, to one researcher, less like a clean rhythm and more like noise from a broken radio. This was supplemented by astrometry, the precise measurement of stellar positions. By tracking the minute dance of these stars across the sky over many years, scientists could begin to map their incredibly complex orbits, like figuring out the steps of 10 dancers on a floor when you can only see them under a strobe light. The confirmation of this system was met with a mixture of sheer disbelief and profound excitement. The initial reaction in the scientific community was one of healthy skepticism. followed by a slow dawning realization that they were looking at something that fundamentally challenged previous models. Before this, the known record holder was a system with 7 or 8 stars, which was already considered an extreme outlier. To find a stable, or at least a temporarily stable, configuration with 10 stars was a monumental step. It forced astrophysicists to go back to their simulations and reconsider the very processes of star formation and gravitational dynamics. It proved that the universe was capable of building structures far more elaborate and intertwined than we had ever dared to imagine, pushing our understanding of cosmic architecture into entirely new and uncharted territory. Now, with the existence of these systems confirmed, we arrive at the next great puzzle, the very thing that makes them so bewilderingly strange: their orbits. If you thought the simple elliptical path of a planet around a single star was easy to understand, prepare to have your mind stretched. The orbital architecture within a Decuple system is a masterpiece of cosmic chaos and precision, a gravitational labyrinth where stars don't just orbit, they engage in an intricate, multi-level dance. Think of it not as a single waltz, but as an entire dance troupe performing different routines on the same stage, all at the same time, with some dancers moving in perfect sync while others seem to be on the verge of spinning off into the wings. This is the heart of the strangeness, a hierarchical structure of unbelievable complexity. At its core, this structure works like a set of cosmic nesting dolls. The most stable arrangement sees stars first pairing off into tight binaries, 2 stars locked in a close, frantic dance around each other. Sometimes a third star will join to form a tight triplet. These pairs or triples then become a single gravitational unit, and they begin to orbit another pair or triplet at a greater distance. This creates a new, larger system, which itself can orbit another cluster, and so on, building up layer by layer until you have a full 10-star family. It's a gravitational pyramid scheme of staggering proportions. The closest analogy we have on Earth is our own solar system, where moons orbit planets and planets orbit the sun, but here every single tier of that structure is made of stars. You have stars orbiting stars that are orbiting other stars that are all moving around a shared center of gravity that might not even be occupied by a physical object. Within this dizzying structure, 2 fascinating phenomena emerge: orbital resonances and chaotic zones. Orbital resonances are the universe's way of creating harmony from chaos. This occurs when the orbital periods of different stars or pairs lock into a simple integer ratio, like 2 pendulums swinging in perfect timed harmony. For example, for every 3 orbits an inner pair completes, an outer pair might complete exactly 1. This gravitational syncing acts as a stabilizing force, a rhythmic handshake that keeps the orbits predictable and prevents the stars from getting too close and disrupting the entire system. It's the precision of a finely tuned clockwork mechanism, with gears of immense size and power ticking away in the void over millennia. But for every zone of perfect resonance, there exists its terrifying opposite, the chaotic zones. These are regions where the gravitational pulls from multiple stars overlap in just the right, or rather wrong, way to create an environment of pure instability. Here, the motion of a star becomes fundamentally unpredictable. It's the celestial equivalent of trying to balance a marble on the peak of a steep, wobbly hill. A tiny, almost imperceptible nudge from a distant stellar cousin can be amplified over time, leading to a catastrophic change. A star wandering into one of these zones can be violently flung out of the system entirely, becoming a rogue star destined to drift alone through the interstellar darkness. Other times, the chaos leads to a dramatic close encounter, where stars swing so near to each other that they violently strip away atmospheres or even trigger the formation of new, tighter binary pairs. This eternal tug of war between the clockwork stability of resonance and the tempestuous anarchy of chaos is what defines the life and ultimate fate of these incredible stellar families. Given the gravitational gymnastics required for stars to coexist, you might assume that planets would be an impossible dream in such a turbulent environment. The sheer gravitational noise, the constant pushing and pulling from so many massive bodies, seems like it would shred any fledgling planet to pieces or fling it into the void long before it could ever form. Yet, in one of the most startling revelations about these systems, astronomers have found that planets not only exist within the chaos, but they also find ways to survive. This discovery completely upends our traditional notions of where planets can form and what conditions they can endure. It turns out that planets in Decuple systems are the ultimate cosmic survivors, finding stable niches in the gravitational storm. These planets achieve stability by locking into very specific protected types of orbits. The most common are what we call circumbinary orbits, where a planet doesn't orbit a single star, but instead circles around a tight binary pair, effectively treating the two stars as a single gravitational center. Imagine a planet gracefully tracing a wide path around a pair of dancers spinning wildly in the middle of a ballroom. It stays far enough away to avoid being knocked off course, held securely by the combined pull of the central duo. For a planet to survive here, it must orbit beyond a critical distance known as the chaos boundary, inside which the changing gravitational forces from the two stars would make any orbit wildly unstable. Scientists have found planets in these configurations, worlds that would experience double sunrises and sunsets, with the two stars sometimes appearing close together in the sky and at other times widely separated, creating a constantly shifting dance of light and shadow. An even more profound orbit is the P-type or circumsystem orbit. In this configuration, a planet doesn't bother with any individual star or pair. Instead, it makes a wide, grand tour around the entire gravitational center of mass of the entire Decuple system. From this distant vantage point, the 10 stars would appear as a tight, brilliant cluster, a single, multifaceted jewel at the heart of its world. The planet's year would be incredibly long, taking perhaps thousands of our Earth years to complete a single revolution, but its orbit would be remarkably stable. This is because from so far away, the complex tugs and pulls of the individual stars largely average out, merging into a single, predictable pull from the system's core. It's the ultimate strategy for survival, staying so far from the fray that the chaos below simply becomes a beautiful, shimmering light show. But what does this mean for the possibility of life? The implications for habitability are as double-edged as a sword. On one hand, a planet in a stable circumbinary orbit around a pair of calm, sun-like stars could enjoy a relatively benign environment, residing within a habitable zone where temperatures might allow for liquid water. However, the location of this zone is not static. As the two stars orbit each other, the distance between them changes, causing the habitable zone to wobble in and out. A planet could be baked when the stars are close and frozen when they are far apart, leading to extreme seasonal shifts on a scale we can barely comprehend. For a planet on a P-type orbit, the sheer distance from the stellar cluster means it receives very little light and heat, likely making it a frozen, barren world unless heated from within by tremendous geological activity. Furthermore, the potential for catastrophic events is ever present. A close gravitational encounter between stars elsewhere in the system could reverberate through the entire architecture, destabilizing a planet's orbit and either ejecting it or sending it on a collision course. Life would need to be incredibly resilient to gain a foothold in such a dynamic and unpredictable neighborhood, making these potential worlds both places of breathtaking beauty and profound danger. This frantic gravitational dance doesn't just rearrange the cosmic furniture, it fundamentally alters the very lives of the stars themselves. While our own sun is expected to burn steadily for about 10 billion years, stars in a Decuple system often face a much more dramatic and accelerated fate. Their lifetimes are not dictated by a slow, peaceful burning of their core fuel, but are instead cut short by the constant, violent attentions of their stellar neighbors. The primary culprit behind this stellar shortening is a process known as mass transfer. In tight binary pairs, if one star evolves faster and swells into a giant, its outer atmosphere can literally spill over onto its companion. This isn't a gentle trickle, it's a raging river of superheated plasma being pulled by gravity from one star to the other, a process that can dramatically change the properties of both. The star losing mass has its life cycle abruptly interrupted, while the star gaining mass is suddenly rejuvenated, flooded with fresh hydrogen that can reignite nuclear fusion in its core with a new intensity. This stolen stellar material can create some of the most bizarre objects in the cosmic zoo. Take the phenomenon of blue stragglers. In a typical star cluster, the most massive, bright blue stars burn out the fastest. But astronomers observing the environments around dense systems have found stars that appear unnaturally blue and young, shining brightly long after all their similar mass peers should have aged into red giants or died. These are blue stragglers, and they are almost certainly the product of stellar vampirism. They are stars that have either merged with a partner or, more commonly, siphoned off so much hydrogen fuel from a companion that they effectively reset their internal clocks. They are the cosmic equivalent of finding a vibrant 40-year-old in a retirement home. Their youthful appearance is a direct result of a dramatic and violent interaction. Beyond simple mass theft, the intense tidal forces in these systems act like a relentless gravitational sandpaper. As stars swing perilously close to one another in their complex orbits, the difference in gravitational pull on the near side versus the far side of a star can become immense. This tidal force can stretch a star into a teardrop shape, stripping away its outer layers without the need for a direct collision. This process slowly erodes the star, casting its material off into space to form intricate, glowing nebulae or simply feeding the interstellar medium. A star that might have lived for billions of years in isolation can have its lifespan cut in half, its outer envelope steadily peeled away until its hot, dense core is exposed prematurely. The most spectacular and violent consequence of these interactions is the potential for premature stellar death. A star's fate is sealed by the mass it has when its core runs out of fuel. By transferring mass between them, stars in a decuple system can push a companion over a critical threshold. A white dwarf, the Earth-sized cinder of a sun-like star, can be given just enough extra mass from a donor star to exceed the Chandrasekhar limit, the point where it can no longer support its own weight. This triggers a cataclysmic thermonuclear explosion, a Type Ia supernova, that utterly annihilates the white dwarf. In a quieter system, this might never happen, but here, the constant gravitational jostling provides the perfect mechanism for this stellar bomb to be triggered. Similarly, a massive star could have its outer hydrogen layers stripped away by a close pass, revealing its deeper, hotter burning layers and potentially accelerating its own collapse into a supernova. The result is that these systems can become cosmic fireworks factories, with stars exploding long before their time, their brilliant but brief deaths lighting up the nebula around them and forever altering the gravitational balance of their entire stellar family. And yet, even with all these violent interactions happening within the system, the most dramatic fate for a star isn't to be consumed or to explode, but to be exiled. This leads us to one of the most profound discoveries about these stellar families. They are prolific factories for rogue stars, the same complex gravitational dance that can bring stars into a tight embrace can, with equal force, violently fling one of their own out into the dark, empty vastness of interstellar space. This isn't a gentle nudge, it's a gravitational slingshot effect of unimaginable power. Imagine a star in a tight inner binary swinging too close to a third, more massive star passing through. The intruder's gravity can act like a catapult, transferring a tremendous amount of orbital energy to the smaller star. In a flash, its velocity skyrockets, not just breaking the bonds of its immediate orbit, but achieving escape velocity for the entire system. It's flung away on a one-way trip, a celestial cannonball shot out of the cosmic fortress it once called home. The speeds these ejected stars can reach are truly mind-boggling. We're not talking about a leisurely drift, we're talking about hypervelocity stars, some clocked moving at over 1,000,000 miles per hour. At that speed, a star isn't just wandering, it's on a blistering trajectory that can carry it clear across the galaxy, from the crowded central bulge to the sparse outer halo, and in some extreme cases, even out into the intergalactic void beyond the Milky Way's gravitational grasp. Detecting these stellar outlaws is a triumph of modern astronomy. They are often found as isolated, lonely points of light moving on trajectories that clearly don't belong to any of the galaxy's standard rotation patterns. By carefully measuring their radial velocity, the speed at which they are moving directly towards or away from us, and their proper motion, their slow drift across the sky, astronomers can trace their paths backward. Incredibly, for several known hypervelocity stars, these cosmic backtracking exercises have pointed a finger directly back to the dense, chaotic environment of the galactic center, a region thought to host its own complex multi-star systems and even a supermassive black hole, both capable of providing the immense gravitational slingshot needed for such an ejection. The significance of these rogue stars extends far beyond their own dramatic stories. They serve as crucial tracers for mapping the hidden architecture of our galaxy. Every hypervelocity star is like a probe launched from a specific location, carrying with it information about the gravitational forces that launched it. By studying their distribution and velocities, astronomers can indirectly weigh the Milky Way's dark matter halo, the invisible scaffold that makes up most of our galaxy's mass. They can test the shape and strength of the galactic gravitational field over vast distances. Furthermore, these ejected stars are not empty-handed. Any planets that were tightly bound to them would be ripped away in the chaotic ejection process, but the star itself carries its entire chemical composition into the galactic wilderness. This means that the heavy elements forged in its core, or in the cores of its former siblings, get a free ride to regions of space that might otherwise be devoid of such materials. In a very real sense, Decuple systems are not just stellar families, they are active participants in galactic ecology, seeding the cosmos with both lone stars and the elemental building blocks for future generations of stars and planets in places they would never otherwise reach. Just when we thought we had a handle on the dynamic nature of these systems, we encounter a phenomenon that turns simple observation into a cosmic puzzle box: the strange and utterly unpredictable variability of their starlight. Far beyond the regular clockwork dimming of a simple eclipsing binary, the light from stars in a Decuple system behaves like a frantic Morse code, sending signals that are a nightmare to decipher. This isn't just one star passing in front of another, it's the combined effect of 10 stars, each with its own orbit and brightness, weaving in and out of view in an infinitely complex celestial tapestry. The result is a light curve, a graph of brightness over time that looks less like a clean, repeating wave and more like the chaotic scribble of a toddler, with dips, peaks, and plateaus appearing at seemingly random intervals. For astronomers trying to model these systems, it's like trying to listen to 10 different songs playing simultaneously from the same speaker, and then being asked to identify every single instrument in every song. The source of this chaos lies in the sheer number of overlapping gravitational influences. Imagine a tight pair of stars, star A and star B, orbiting each other every few days, creating a predictable pattern of eclipses. Now introduce a third star, star C, which orbits this pair on a longer, inclined orbit. Star C will regularly pass behind or in front of the inner binary, but its own light also adds to the total brightness of the system. Sometimes star C might eclipse star A just as star A is itself being eclipsed by star B, creating a profound, extended dip in light. Other times, the reflected light from the heated sides of close stars can cause a slight brightening. The possibilities for combination are nearly endless, with the light from each star being periodically blocked, amplified, or distorted by the motions of the others. There's no clean, repeating pattern because the orbits are not perfectly synchronized. Their gravitational interactions cause slight changes in their periods over time, a phenomenon known as transit timing variations on a massive stellar scale. This makes it incredibly difficult to isolate the signal of any single star or event from the cacophony. This stellar noise pollution creates a particularly insidious problem. It can completely mask the presence of planets. The primary method for finding exoplanets is the transit method, where we watch for the telltale, periodic dimming of a star as a planet passes in front of it. In a quiet, single star system, that tiny dip is a clear signature. But in the tempest of a decuple system, that same small dip is like trying to hear a single whisper in a roaring hurricane. The planet's signal is drowned out by the constant, erratic brightening and dimming caused by the stellar dance. A dip that might be a planet could just as easily be a faint, distant stellar cousin briefly eclipsing part of a brighter star, or a temporary flare from a turbulent red dwarf within the system. Confirming a planet requires seeing that dip repeat with perfect regularity. But in this environment, the gravitational nudges from so many stars can easily perturb a planet's orbit, making its transits irregular and therefore indistinguishable from the background stellar variability. It means that potentially habitable worlds could be hiding in plain sight, their faint signals lost in the brilliant, chaotic glare of their 10 parent suns. Another layer of strangeness in these stellar families comes from the bizarre and seemingly mismatched couples they contain. Within a single decuple system, you can find stellar pairings that defy conventional wisdom, like a cosmic giant living next door to a stellar dwarf. Imagine a searingly hot, brilliant blue O-type star, a behemoth that can be over 100 times the mass of our Sun and shine with the power of 1,000,000 suns, locked in a gravitational embrace with a faint, cool red dwarf, a star so dim and small it's barely more than a glowing ember in comparison. These are not just odd neighbors, they are direct partners orbiting one another in a union that seems almost impossible given their vastly different origins and life expectancies. How does such a pairing even come to be? The answer lies in the chaotic nurseries where these systems are born. Decuple systems don't form in quiet, orderly corners of space. They emerge from the deepest, densest parts of giant molecular clouds, regions of frantic star formation where thousands of stars are being born in close proximity. In this cosmic mosh pit, gravitational encounters are constant and violent. Stars don't get to choose their partners based on similarity. They are thrown together by the random churn of the cloud's collapse. A massive, hot O-star might form at the center of a local density peak, while a handful of smaller, cooler stars form nearby. As the gas cloud dissipates, the complex gravitational dance begins, and through a series of close passes and captures, the massive star can easily capture one of the smaller ones into a tight orbit. The sheer density of the environment makes these unlikely gravitational captures not just possible, but almost expected. It's a stellar arranged marriage orchestrated by the raw, unfeeling laws of physics in a turbulent birthplace. These exotic pairings act as unique cosmic laboratories, offering insights we could never gain from studying isolated stars. The intense ultraviolet radiation from the O-type star, for example, relentlessly batters the atmosphere of its red dwarf companion, potentially stripping it away and creating a spectacular, glowing tail of ionized gas streaming behind it like a cosmic windsock. This process, known as radiative stripping, gives us a front-row seat to stellar erosion in action. Furthermore, the gravitational pull of the massive star can induce tidal forces on the red dwarf, heating its interior through friction and potentially triggering heightened stellar activity, like powerful flares and spots that would not occur if the small star were left in peace. By observing this lopsided relationship, we learn how extreme environments can alter the fundamental behavior and evolution of stars. Even more extreme than a pairing of stars in different life stages is the presence of a stellar corpse. We have evidence of systems that contain a neutron star, the incredibly dense, city-sized remnant of a supernova explosion, orbiting alongside perfectly ordinary, hydrogen-burning main sequence stars similar to our Sun. This creates a surreal cosmic scenario, a tiny, dead object with the mass of an entire star squeezed into a sphere just a few miles across, whipping around a vibrant, living sun. The formation of such a system is a story of survival against all odds. It begins with a tight binary pair of two massive stars. The more massive one explodes first in a supernova. This explosion is inherently asymmetric. The dying star gives a powerful kick to the newborn neutron star, rocketing it through space at high velocity. In most cases, this kick would instantly break the gravitational bond, sending the neutron star flying away alone. But in the densely packed core of a Decuple system, there's a chance, a small but real chance, that the surrounding gravitational pull from the other 8 stars is strong enough to act as a glue, holding the entire system together even through the violent trauma of a supernova. The neutron star remains bound, a silent, dense monument to a past cataclysm, now orbiting its former partner, which may itself be nearing the end of its life. The presence of these stellar zombies opens up a new window into fundamental physics. A neutron star in a multi-star system can become a pulsar, beaming radiation like a lighthouse as it spins. By meticulously timing the pulses from such a pulsar as it moves through the complex gravitational field of its many stellar companions, astronomers can perform the most precise tests of Einstein's theory of general relativity. They can watch for subtle changes in the pulse timing caused by the warping of spacetime, effects that are magnified in such a rich gravitational environment. These systems become natural accelerators and laboratories for probing gravity itself, offering a level of precision impossible to achieve in any Earth-based experiment. Each unlikely pairing, whether it's a giant and a dwarf or a living star and a dead one, tells a unique chapter in the story of its system's violent birth and resilient existence, proving that in the cosmic chaos of a Decuple system, the most improbable relationships can not only form but can also become the key to unlocking the universe's deepest secrets. Now consider the raw materials of creation itself. In a single star system like our own, the process of planet formation is thought to be a relatively orderly affair. A swirling, flattened disk of gas and dust encircles the young star, and within this disk, dust grains gently collide and stick together, eventually building up into planets over millions of years. But place that same disk into the gravitational maelstrom of a Decuple system, and order is replaced by sheer pandemonium. The resulting structures are not simple, placid frisbees of dust. They are colossal, warped, and twisted sculptures of debris, exhibiting features that look more like abstract art than astronomical phenomena. These are the intricate dust and debris disks of Decuple systems, and they represent one of the most visually stunning and scientifically confounding discoveries in this field. The key to their bizarre shapes lies entirely with the relentless gravitational tug of war from the 10 stars. A single star provides a single, central gravitational anchor, allowing a disk to settle into a smooth, symmetric ring. But with multiple stars orbiting both close in and farther out, the disk is subjected to a constantly changing gravitational landscape. It's like trying to form a neat sand pattern on a sheet of glass while 10 different people are shaking the table beneath it. The gravity from the stars carves out gaps, shepherds dust into narrow rings, and pulls vast streams of material into elegant, grand design spirals that stretch across distances much larger than our entire solar system. In some observed systems, the disk isn't even centered on any one star. It can be offset, lopsided, or even exhibit sharp, asymmetrical arcs, as if a giant cosmic knife has come along and sheared off one side. These are the direct fingerprints of stellar gravity, a permanent record of the complex orbital dances happening within. This chaotic environment has a profound and paradoxical impact on planet formation. On one hand, the intense gravitational stirring can be a destructive force. The same forces that create spiral arms can also dramatically increase the relative speeds at which dust particles and larger planetesimals collide. Instead of gently sticking together, these collisions become hypervelocity impacts, shattering nascent planets back into dust and gravel. It creates a collisional grinding environment where it becomes incredibly difficult for objects to grow beyond a certain size. You can think of it as a cosmic demolition derby, where every participant is constantly being smashed apart before they can build anything stable. This might suggest that planets are unlikely to form here, yet we know they can exist. So, how do they do it? The answer seems to be that destruction and creation are two sides of the same coin in these systems. While the outer regions of a disk may be too violent for growth, the gravity of the stars can also create safe havens, protected gravitational niches where the chaos is minimized. For instance, a planet might form in the dense, compressed material of a spiral arm itself, or within a gap cleared by a stellar companion where the local environment is quieter. Furthermore, the very process of collisional grinding, while destructive, also creates an immense amount of fine dust. This dust is the essential feedstock for the next generation of planet building. It's a brutal, cyclical process. Large objects are shattered, creating dust that then clumps together again elsewhere, in a different part of the disk under different gravitational rules. Planet formation in a decuple system isn't a linear, peaceful progression. It's a frantic, stop-start process happening in isolated pockets of temporary stability, a testament to the relentless creativity of the universe even in the most hostile of environments. And now we arrive at a discovery that connects these stellar juggernauts to one of the most profound predictions of modern physics. We've seen how the stars in these systems engage in a violent, chaotic dance, but it turns out their motion doesn't just affect their immediate surroundings, it literally shakes the fabric of the cosmos itself. These tight binaries within decuple systems have been identified as veritable factories for gravitational waves, the elusive ripples in space-time first predicted by Albert Einstein over a century ago. Imagine space-time not as a static stage, but as a flexible, elastic fabric. When massive objects like stars orbit each other at incredible speeds, they don't just move through this fabric, they warp and stretch it, sending out waves of distortion that travel outward at the speed of light. It's akin to the wobbling of a bowl of gelatin when you tap the side, a cosmic vibration born from pure motion. The key to why these systems are such potent sources lies in the incredible forces at play in their tightest binaries. When two dense stellar remnants like a pair of white dwarfs, neutron stars, or even black holes are locked in a close, frantic orbit, they are essentially whipping space-time around them into a frenzy. The energy required to power this cosmic distortion is drawn directly from their orbital energy. This results in a slow but relentless inward spiral. As they lose energy to these space-time ripples, the stars draw closer together, their orbit shrinks, and their speed increases, which in turn makes them radiate gravitational waves even more powerfully. It's a runaway process, a feedback loop of gravitational radiation that ultimately dictates the binary's final fate. In a quieter, isolated system, this process might take billions of years, but within the turbulent environment of a decuple system, the timeline can be dramatically accelerated. Gravitational interactions with other stars in the family can constantly tighten these inner binaries, feeding them into the gravitational wave grinder far more efficiently than they would manage on their own. For decades, detecting these faint whispers from the universe was beyond our reach. But a new era of astronomy is dawning, one that will listen to the cosmos rather than just look at it. The Future Laser Interferometer Space Antenna, or LISA, mission is poised to be our most sensitive ear yet for these low-frequency cosmic vibrations. Unlike ground-based detectors, which are limited by terrestrial noise and can only hear the final, high-frequency chirps of the most massive mergers, LISA will be a fleet of 3 spacecraft orbiting the Sun in a perfect triangle millions of kilometers on a side. By firing lasers between them and measuring the minuscule changes in distance changes smaller than the width of an atom caused by a passing gravitational wave, LISA will open up a low-frequency window on the universe. This is the perfect band to hear the continuous, rising hum emitted by the tight stellar binaries within Decuple systems. While we might never resolve an individual Decuple system's 10-star hum from across the galaxy, the collective cacophony of thousands of such systems throughout the Milky Way will create a stochastic gravitational wave background, a steady murmur underlying all other signals, a testament to the sheer number of these dynamically heated binaries. Listening to this gravitational soundtrack will provide us with a revolutionary new way to probe the internal dynamics of these systems. By analyzing the specific frequencies and amplitudes of the waves, astronomers will be able to infer the masses of the orbiting objects and the tightness of their orbits with unparalleled precision. This data acts like a cosmic fingerprint, revealing the population of ultra-compact binaries that are otherwise invisible to traditional telescopes. But the real power comes from observing how these wave signals change over time. If LISA detects a binary that is inspiraling faster than predicted by general relativity alone, it would be a clear sign that the system is not isolated. That extra kick in the spiral is the direct signature of a third, or even a fourth, star gravitationally perturbing the binary, constantly squeezing it and driving it toward merger. LISA wouldn't just be hearing a binary, it would be hearing the gravitational influence of the entire stellar family encoded in the wave signal, allowing us to map the intricate hierarchical structure of a Decuple system from thousands of light years away. This brings us to the ultimate question that these gravitational waves can help answer: the final fate of these systems. The relentless radiation of gravitational waves inevitably drives the tightest binaries toward a dramatic merger. For double white dwarfs, this could result in a cataclysmic explosion known as a Type Ia supernova, the very kind used as standard candles to measure cosmic distances. For double neutron stars, the merger unleashes a kilonova, a blasting furnace where the heaviest elements in the universe, like gold and platinum, are forged in an instant. By counting the rate of these mergers through their gravitational wave signals, we can determine if Decuple systems are a primary source of these cosmic elements. Furthermore, the same gravitational interactions that can create these ultra-tight binaries can also tear them apart. A close encounter with another star could destabilize a binary, either hurling it out of the system as a runaway pair or disrupting it entirely. The gravitational wave background will therefore tell us the balance between creation and destruction within these stellar families, revealing whether they are ultimately stable structures or temporary, flash-in-the-pan arrangements destined to dissolve into a cascade of mergers and ejections, seeding the galaxy with stellar remnants and newly forged elements in their spectacular demise. But for all the incredible complexity we've explored, not every dense grouping of stars earns the permanent title of a Decuple system. In fact, some of the most telling discoveries are the ones that got away. The stellar collectives that were initially thought to be these rare 10-star families, but upon closer inspection, revealed themselves to be something else entirely. These are the so-called failed Decuple systems, and they tell a story just as important as the successful ones, a narrative of dissolution, mistaken identity, and the inherent fragility of cosmic architecture. Consider a system that presents at first glance all the hallmarks of a dense family. Through a telescope, you see a tight cluster of 10 distinct points of light, all moving together through space. The initial radial velocity measurements show a jumble of wobbles, and the light curve is a chaotic mess. It looks, for all intents and purposes, like the real deal. But then, with more advanced instruments and years of patient tracking, the picture begins to change. What astronomers often find in these cases is that they were not looking at a single, gravitationally bound family, but at a chance alignment. They were observing an optical double, or more accurately, an optical multiple. This is when two or more distinct star systems, each perhaps a simple binary or triple, happen to lie along the same line of sight from Earth. They appear to be neighbors, but in reality, one system could be hundreds of light years behind the other, with no gravitational connection whatsoever. It's the cosmic equivalent of seeing a person standing in front of a distant mountain. They appear to be right next to each other from your vantage point, but they are in fact separated by a vast gulf of space. Unraveling this illusion requires incredibly precise parallax measurements from observatories like Gaia, which can measure the tiny shifts in a star's apparent position as Earth orbits the Sun, allowing us to calculate their true distances with stunning accuracy. When the data comes in, the 10 points of light separate into a foreground group of 4 stars and a much more distant group of 6, shattering the Decuple hypothesis. Other systems represent not a case of mistaken identity, but one of fleeting existence. These are young, fragile associations still in the process of deciding their own fate. Born in the violent turmoil of a stellar nursery, a group of a dozen or more protostars may be flung into a loosely bound configuration. For a short while, perhaps only a few million years, a mere blink in cosmic time, they orbit a common center. But their gravitational bonds are weak, their velocities are just a little too high, and their initial positions are just a little too unstable. They are what astronomers call a dissolving cluster. The constant, gentle gravitational tugs from outside the group, from the rest of the galaxy, or from close encounters within the group itself, slowly pry the stars apart. One by one, they drift away, their shared motion dissipating until all that's left is a stream of stars, a faint trail of once siblings now destined to travel the galaxy alone. Finding such a system in its death throes is like catching a house of cards as it collapses. It provides a direct snapshot of the destructive forces that prevent most large systems from ever achieving long-term stability. The existence and prevalence of these failed systems deliver a crucial insight. High multiplicity star systems might be far more common at birth than we ever suspected, but they are also profoundly ephemeral. The default state of cosmic formation in dense clouds seems to be to produce a lot of stars in close proximity. The real cosmic puzzle, then, isn't necessarily how a decuple system forms, but how any of them manage to survive. Their long-term stability hinges on a very delicate and apparently rare set of initial conditions. The stars must be born with just the right amount of rotational energy. Their orbits must fall into those stabilizing resonant chains early on, and their mass ratios must be such that violent interactions are minimized. It's a cosmic lottery with incredibly slim odds. A system that starts with 12 stars might quickly eject 2 in a close encounter, settling down into a more stable but lower multiplicity configuration of 10. Another system that starts with 10 might be inherently unstable from the outset, destined to shed stars over hundreds of millions of years until it becomes a simpler sextuple or quintuple system. The decuple systems we see today are the exceptional survivors, the cosmic equivalents of a tower that remained standing after an earthquake leveled all the others around it. This changes our entire perspective on stellar demographics. Instead of being rare artifacts, decuple systems could be the visible tip of a vast iceberg, the few successful outcomes from a much larger population of short-lived stellar families that quickly disintegrate. This idea is supported by computer simulations of star formation. When astronomers run models that replicate the conditions inside a giant molecular cloud, the result is often a profusion of complex, high-multiplicity systems. But when they fast-forward the simulation, the majority of these systems rapidly unravel. Stars are ejected, binaries are broken, and the complex hierarchy collapses into simpler, more stable arrangements. The simulations show that achieving a configuration that can last for billions of years is the true anomaly. This suggests that the galaxy is likely teeming with the remnants of these failed systems, solitary stars and tight binaries that were once part of much larger families, their tumultuous pasts now hidden, revealed only by their unusual velocities or chemical compositions that hint at a violent ejection long ago. Every rogue star we discover might not just be a random outlier, but a refugee from a decuple system that never was. Moving deeper into the chemical fingerprints of these systems reveals another layer of their chaotic past. When astronomers point their spectrographs at the individual stars within a decuple family, they often find atmospheric compositions that defy standard stellar recipes. A star that, by all rights, should have a certain amount of an element like lithium might possess 100 times more, or conversely, be almost completely devoid of it. These unusual chemical abundances are like forensic evidence left at a cosmic crime scene. They are the indelible marks of a system's violent history, telling stories of stellar cannibalism, catastrophic explosions, and elemental pollution that occurred billions of years ago. Take lithium, for instance. This fragile element is easily destroyed in the hot furnaces of stellar interiors. In a solitary star like our Sun, the lithium present at its birth is gradually depleted over its lifetime as convection cycles the surface material down into the hotter core, where it gets fused into heavier elements. So when we see a star, especially a hot, massive one, that has an unusually high abundance of lithium in its atmosphere, it's a major red flag. It indicates that this star has recently received a fresh supply of lithium from an external source. In the crowded environment of a decuple system, the most likely culprit is mass transfer. A lower mass companion star, which burns its fuel more slowly and preserves its surface lithium, can have its outer layers lithium and all stripped away and dumped onto the more massive star. The receiving star's atmosphere becomes artificially enriched, its chemical clock reset in a way that would be impossible if it had evolved in isolation. It's the stellar equivalent of a blood transfusion, where one star's composition is permanently altered by the material of its neighbor. The opposite scenario is just as revealing. Finding a star that is peculiarly deficient in certain elements, particularly those that are normally common, can point to a different kind of dramatic event. Imagine a star that was once part of a tight binary pair with a much more massive partner. That massive partner lived fast and died young, exploding as a supernova. The sheer blast wave from that explosion, moving at a significant fraction of the speed of light, would have slammed into the surviving star. This isn't a gentle interaction. It's a cosmic pressure washing that can literally blow away the star's outer atmosphere, stripping it of the lightweight elements like hydrogen and helium, and leaving behind a surface that is unusually rich in the heavier elements that were deeper in its interior. We see stars with atmospheres dominated by helium and carbon, looking almost like the exposed cores of much older stars. This supernova stripping provides direct evidence that a stellar sibling once existed right next to them and met a violent end, its death permanently scarring the survivor. Beyond lithium, anomalies in heavier metals act as a chronicle of the system's most cataclysmic events. Some stars in these systems show a significant overabundance of elements like europium, gold, and platinum. These particular elements are not forged in the slow burn of ordinary stellar cores. They are created almost exclusively in the incredibly violent conditions of a kilonova, the merger of two neutron stars. Discovering a star enriched with these R-process elements is like finding gold dust on the shores of a river. It tells you that a massive gold deposit must exist upstream. In this case, the upstream event was a neutron star merger that happened within the system long ago. The explosion would have sprayed the surrounding space with a cloud of newly synthesized heavy elements, and some of that material would have settled onto the surfaces of other stars in the family as they plowed through the debris. The enriched star we see today is a living record of that ancient universe-forging collision, a silent witness to one of the most energetic events in the cosmos. These chemical clues allow astronomers to perform a kind of cosmic archaeology, piecing together the family tree of a decuple system long after the formative events have concluded. By measuring the precise ratios of different elements in each star, they can begin to model the system's history. A star with high lithium and carbon might have been the recipient of mass from a dying asymptotic giant branch star. Another with high iron content but low levels of certain lighter elements might have been polluted by a type Ia supernova from a white dwarf companion. By mapping these chemical signatures across the different members of the system, scientists can start to identify which stars were once binary partners, which ones were distant observers, and which former members are now missing, their existence inferred only by the chemical scars they left behind on their siblings. It transforms a random collection of points of light into a dynamic historical document, written not in ink but in the elemental composition of starlight. As we shift our gaze from the chemical stories locked inside individual stars to the gravitational forces governing the entire system, we approach perhaps the most profound and speculative mystery of all. Astronomers studying the precise motions of stars in some of the most distant decuple systems have stumbled upon a gravitational anomaly, a discrepancy so puzzling it points toward the most elusive substance in the universe. The math simply doesn't add up. When they calculate the total gravitational pull needed to keep 10 stars whirling around each other in their observed orbits, they find that the visible mass of the stars themselves is not enough to provide the necessary glue. There appears to be a tremendous amount of extra, unseen mass holding the system together, an invisible gravitational anchor. This missing mass problem leads to a startling and controversial hypothesis that these complex stellar families might be shrouded in their own private, localized halos of dark matter. The technique used to uncover this ghostly presence is a cornerstone of astronomy, a kind of cosmic accounting called gravitational mass modeling. It works on a simple principle. The speed of a star in a stable orbit is a direct measure of the total mass inside its orbit. Just as the planets in our solar system move faster the closer they are to the Sun's immense gravity, the stars in a decuple system trace out paths dictated by the collective gravity they feel. By meticulously mapping the velocities and orbital radii of all 10 stars, astronomers can use Newton's laws to calculate the system's total mass. Again and again for certain distant systems, the result is the same. The mass you get from adding up the light of all the stars is far less than the mass you get from watching their motion. This discrepancy isn't a small accounting error. It can be a factor of 2, 5, or even 10 times more mass than what is visibly shining. This is the same fundamental clue that first revealed dark matter on the scale of entire galaxies, but now we're seeing it potentially play out on the scale of a single, sprawling stellar family. If dark matter is indeed concentrated around these systems, it would fundamentally rewrite our understanding of how this mysterious substance is distributed throughout space. The prevailing cosmological model, known as lambda cold dark matter, suggests that dark matter forms an immense, diffuse web across the universe, with galaxies forming at the densest nodes of this cosmic scaffolding. It doesn't typically predict that small, isolated star systems would possess significant private halos of their own. The discovery of such halos would mean that dark matter can clump on much smaller scales than previously thought, a finding that would send theorists back to their drawing boards. It would suggest that the initial conditions of the universe allowed for tiny, dense knots of dark matter to form, and that these decuple systems didn't just form from a cloud of gas, but actually congealed at the heart of one of these invisible gravitational seeds. The stars and their complex dance would be a mere side effect, the visible tracer of a much larger, hidden cosmic structure. This idea, while compelling, is fiercely debated within the scientific community. Skeptics propose other, more conventional explanations for the missing mass. One strong possibility is that the system is simply harboring a large number of faint, failed stars. Brown dwarfs, objects too massive to be planets but not massive enough to ignite sustained hydrogen fusion, could be littering the system. These failed stars emit very little light, especially in the optical range, but they still carry significant mass. A population of dozens of brown dwarfs, along with a menagerie of rogue planets and cold dust, could potentially account for the extra gravitational pull without needing to invoke dark matter at all. Another possibility is that the system contains stellar remnants that are exceptionally difficult to detect, like isolated black holes or cold, aged neutron stars that have faded into near invisibility. Before we can confidently claim a dark matter detection, astronomers must first rule out this entire unseen population of ordinary, dim celestial objects. The hunt for the truth is driving the development of revolutionary observation techniques. To find these dim objects, astronomers are turning to the most sensitive infrared telescopes, like the James Webb Space Telescope. In the infrared, cool brown dwarfs and dusty debris glow brightly, allowing us to take a more complete census of the system's true stellar and substellar population. At the same time, a phenomenon called gravitational microlensing offers a unique way to probe for invisible mass. If one of these faint, unseen objects within the Decuple system passes directly in front of a more distant background star, its gravity will act as a lens, briefly magnifying the background star's light. By monitoring for these telltale, temporary brightenings, astronomers can literally count the number of invisible massive objects drifting through the system, providing a direct census of the proposed brown dwarf or rogue planet population. If these searches come up empty and the missing mass problem persists even after a thorough search for dim objects, the case for a localized dark matter halo becomes dramatically stronger. The implications of confirming such a halo would be nothing short of revolutionary for both astronomy and physics. For the first time, we would have a small-scale, relatively simple laboratory in which to study dark matter's properties. We could observe how this invisible halo influences the dynamics of the stars over time, potentially revealing how dark matter particles interact with each other through forces other than gravity. Does the halo have a dense, sharp edge, or does it gradually fade away? Does its shape perfectly mirror the distribution of the stars, or is it offset, showing that dark matter and ordinary matter can be pulled apart by gravitational interactions? The answers to these questions would provide critical clues to the very nature of the dark matter particle itself, potentially ruling out whole classes of theoretical candidates. Furthermore, if dark matter is indeed binding these systems, it would explain their incredible longevity. The invisible halo would act as a gravitational cushion, absorbing the energy from close stellar encounters and preventing the system from flying apart. This could be the ultimate secret to their survival, the hidden hand that guides the chaotic dance and allows these magnificent 10-star families to endure for billions of years. Another astonishing feature astronomers have spotted extending from some of these stellar families are enormous, ribbon-like structures that flow out into space for incredible distances. These are tidal tails, vast streams of gas and orphan stars that can stretch for hundreds of light years, appearing like cosmic contrails left behind by the system's turbulent journey. They are not random clouds, they are the direct result of gravitational tides, the same force that causes ocean tides on Earth but operating on a truly colossal scale. These majestic structures form in two primary ways, both tied to the relentless gravitational forces at play in a crowded galactic neighborhood. The first is through internal violence. Within the Decuple system itself, close encounters between stars can generate powerful gravitational slingshots. When two stars swing perilously close, they can stretch each other with their gravity, pulling long streams of superheated plasma from their outer atmospheres. If a star is ejected from the system as a hypervelocity runaway, it can drag this stream of its own stolen material with it, creating a single, brilliant tail blazing a trail through interstellar space. The second, and often more dramatic, formation method comes from external harassment. Imagine the entire Decuple system, a compact cluster of 10 stars, experiencing a close fly-by from another star cluster or even a massive, dense molecular cloud. As this external mass passes, its gravity tugs more strongly on the side of the Decuple system closest to it and more weakly on the far side. This difference in pull stretches the entire system, much like pulling on a ball of cotton candy causes it to form long, wispy strands. Stars and gas that were already loosely bound on the outskirts of the system are the most vulnerable. They get caught in this gravitational tide and are pulled away, not with enough force to achieve escape velocity all at once, but enough to drift slowly out of the system's gravitational grip, forming two distinct tails. One tail is pulled ahead of the system in its orbit, and the other is dragged behind, creating a characteristic and beautiful V-shape that points like an arrow to the system's direction of travel. What makes these tidal tails so invaluable to scientists is that they act as a perfect fossil record, preserving the system's dynamical history in a way the central cluster itself cannot. The central stars are constantly interacting, their orbits changing and their recent past overwritten by new encounters. But the material in the tidal tails, once ejected, is essentially frozen in time. It continues to drift through space, its motion dictated almost entirely by the gentle, predictable gravity of the galaxy as a whole. By studying the exact shape, length, and density of these tails, astronomers can perform a kind of cosmic archaeology. They can run computer simulations backward in time, adjusting the parameters until the model produces a tidal tail that matches the one they observe. This process reveals critical details about the event that created it, such as the mass and speed of the object that caused the disruption and exactly when the encounter happened, millions or even billions of years ago. Furthermore, the chemical composition of the stars within these tidal tails tells its own story. If the stars in a tail have a similar chemical fingerprint to each other but are distinct from the stars remaining in the core of the Decuple system, it suggests that the tail was formed from a single, cohesive group that was stripped away together, perhaps a former binary pair that was torn apart. Conversely, if the tail stars have a wide variety of compositions, it indicates they were random members plucked from throughout the system, revealing something about the internal mixing before the disruption occurred. These streams are more than just beautiful accidents. They are dynamic archives chronicling the gravitational shocks and close calls that have shaped the life of the stellar family, offering a unique window into events that would otherwise be lost to time. Yet another puzzle emerges when astronomers try to take a complete census of these stellar families, finding a notable and perplexing absence. Theories of star formation suggest that when a giant molecular cloud collapses, it should produce a full spectrum of objects from brilliant, massive stars down to dim, failed stars known as brown dwarfs. These brown dwarfs occupy a curious middle ground. They are too massive to be considered planets, but not massive enough to ignite sustained hydrogen fusion in their cores. They are cosmic in-betweeners, and according to all our models, they should be incredibly common, especially in the densely packed environments where Decuple systems form. Yet when scientists search for them within these 10-star families, they come up largely empty-handed. It's a genuine cosmic missing persons case, or rather, a missing object case where the expected population of substellar bodies has seemingly vanished without a trace. This discrepancy points toward a fundamental gap in our understanding of how star formation operates under extreme conditions. In a quieter stellar nursery, like the one that gave birth to our Sun, the process is relatively straightforward, with a distribution of masses that follows a predictable pattern. You get a few high-mass stars, a larger number of medium-mass stars like our Sun, and a veritable swarm of low-mass stars and brown dwarfs. This is known as the initial mass function, and it's a rule that has held up well in most parts of the galaxy. But the intense, crowded environment of a decuple system's birthplace appears to break this rule. The sheer density and frantic gravitational interactions seem to create a biased outcome, favoring the formation of stars that can hold their own in the chaos, while somehow suppressing or eliminating the smaller, more fragile brown dwarfs. It's as if the cosmic assembly line in these regions is configured only to produce heavyweight champions, skipping the lighter contenders entirely. One of the most compelling hypotheses for this absence is that the brown dwarfs were indeed formed, but they were almost immediately evicted from the neighborhood. In the gravitational mosh pit of a young decuple system, stability is a luxury reserved for the most massive players. Brown dwarfs, with their relatively low mass, are like lightweight balls in a game of cosmic pinball. They are incredibly susceptible to gravitational slingshots. A close encounter with a much more massive star, or a complex interaction between several stars, can easily transfer enough kinetic energy to a brown dwarf to fling it out of the system at high velocity. These ejected brown dwarfs would then become lonely, drifting nomads in interstellar space, virtually invisible to our telescopes because of their intrinsic dimness. In this scenario, the decuple systems we see today are not the complete families they once were. They are the survivors, the heavy stars that manage to gravitationally bully their smaller siblings out of the family home, leaving behind a system curiously devoid of these substellar objects. An alternative possibility is that the conditions for forming brown dwarfs are simply not met in these frantic environments. The process of forming a brown dwarf is thought to require a small, relatively isolated core of gas to collapse on its own. But in a region so dense with forming stars, the intense radiation pressure from massive, brilliant O-type stars could literally strip away the gas from these smaller cores before they have a chance to fully coalesce. Imagine trying to build a sandcastle while standing next to a powerful fan. The very material you're trying to gather is constantly being blown away. Furthermore, the gravitational tides from so many large, nearby protostars could tear apart these nascent brown dwarf cores, preventing them from ever reaching a stable configuration. It's a formation bottleneck where the environment is so hostile that the standard star formation recipe fails to produce its full range of expected outcomes, resulting in a top-heavy system from the very beginning. Of course, there is also the very real challenge of detection. Brown dwarfs are notoriously difficult to spot. They emit most of their faint light in the infrared part of the spectrum, and when they are located close to the blinding glare of multiple bright stars, distinguishing their signal becomes an extraordinary technical challenge. It's like trying to spot a single, dim firefly hovering right next to 10 powerful searchlights. Current telescopes simply may not have the contrast resolution to pick out these incredibly faint objects from the overwhelming stellar glare. The upcoming observations from the James Webb Space Telescope, with its unparalleled infrared sensitivity, are poised to test this hypothesis directly. If Webb peers into these systems and still finds a striking lack of brown dwarfs, the case for their genuine absence will become much stronger, forcing a significant revision of our star formation models for the most extreme cosmic environments. Now, let's turn our attention from the gravitational forces shaping these systems to the titanic rivers of energy they pour out into space. A star is not a quiet, static object. It is a raging furnace that constantly blows a hurricane of charged particles out into the void. This is the stellar wind, a supersonic flow of material streaming from a star's upper atmosphere. In a peaceful system like our own, the solar wind is a relatively gentle breeze. But in a decuple system, you don't have just one breeze. You have 10 different stellar hurricanes all blowing at once, each with its own intensity and direction, and they are all colliding with one another in a chaotic, high-energy maelstrom. The discovery of these colliding winds has revealed that the space between the stars in these families is not empty at all, but is instead a violent, dynamic battleground of clashing energies. When these powerful winds slam into each other, the result is nothing short of spectacular. The collision doesn't create a gentle mixing because the winds are moving faster than the speed of sound in the interstellar medium. They create a shock front. Think of two fire hoses being aimed directly at each other. At the point where the streams meet, there is a turbulent, incredibly hot region of compressed and heated gas. In space, these shock fronts can heat the colliding material to temperatures of tens of millions of degrees, so hot that it doesn't glow with visible light, but instead radiates intensely in X-rays. This means that while a decuple system might look like a beautiful cluster of points in an optical telescope, when viewed with an X-ray observatory, it transforms. It blossoms into a tangled web of brilliant, high-energy filaments and arcs, a luminous map of where these stellar hurricanes are fighting for dominance. The entire volume of the system can be filled with this diffuse, multimillion-degree plasma, making it a persistent, powerful source of X-ray radiation, a testament to the continuous violence happening in the spaces between the stars. These interactions don't just create hot gas, they sculpt the surrounding nebula into breathtaking and complex structures. The pressure from the colliding winds can sweep up cooler, slower-moving gas and dust from the interstellar medium, compressing it into intricate shells, bubbles, and pillars. In some systems, the combined wind from a tight binary pair can carve out a vast cavity around them, while the wind from a more distant, massive star crashes into that cavity's wall, creating a brilliant, curved shock wave that glows in the infrared. The resulting nebulae are not the serene, static clouds we often see in posters. They are dynamic and short-lived sculptures, constantly being reshaped by the changing winds as the stars move along their orbits. A particularly dramatic configuration occurs in systems with a Wolf-Rayet star, a massive, evolved star with an exceptionally powerful and fast wind. When this wind collides with that of a massive O-type companion, it can generate a shock front so intense and focused that it produces a constant, high-energy roar detectable across interstellar distances, a beacon of stellar violence. This relentless barrage of stellar winds has a profound and often destructive influence on the very process of planet formation. A young star is typically surrounded by a protoplanetary disk, a vast, rotating frisbee of gas and dust where planets are born. In a quiet environment, this disk can survive for several million years, giving dust grains enough time to gently clump together and build planets. But in a decuple system, a young star's disk is subjected to a continuous sandblasting from the winds of its 9 stellar siblings. The effect is like placing a delicate sand sculpture in the path of a leaf blower. The intense radiation pressure and the physical drag from the wind particles literally strip the disk away, eroding it from the outside in. This process, known as photoevaporation, can truncate the disk dramatically, cutting off its outer regions and robbing it of the raw materials needed to form giant planets like Jupiter. In extreme cases, the entire disk can be stripped away in less than 1 million years, effectively shutting down planet formation before it even has a chance to properly begin. This creates a powerful selection effect within these chaotic stellar families. It means that any planet that does manage to form must do so incredibly quickly, or it must form in a very specific protected location. A planet forming in the inner, denser part of a disk might survive the external wind erosion, while any potential planets forming farther out are simply scoured away. This could explain why we might find compact systems of rocky, terrestrial planets close to their stars in these environments, while the more distant, colder realms where gas giants typically form are left barren. The survival of a planetary disk, and therefore the potential for planets, becomes a race against time, dependent on how quickly the planets can coalesce before the stellar winds from the most massive members of the system blow the cosmic cradle away. The observable signatures of these phenomenal processes are written across the electromagnetic spectrum, but they require specialized eyes to see. As we mentioned, the multimillion-degree shock fronts reveal themselves most brilliantly in X-rays. Space-based observatories like Chandra and XMM Newton have been crucial in mapping these high-temperature collisions, showing us the intricate architecture of the wind-wind interactions. Meanwhile, the cooler, swept-up material in the nebulae glows in the infrared, a domain where telescopes like Spitzer and now the James Webb Space Telescope excel. In radio wavelengths, we can detect the synchrotron radiation emitted by electrons spiraling at near light speed along magnetic fields that are amplified and tangled within the shock fronts. By combining these different views, astronomers can create a multi-dimensional picture of the system. They can calculate the speed and density of the individual winds, measure the immense energy being released in the collisions, and even trace how these structures change over time as the stars continue their complex dance. This truly is a case where seeing the universe in different kinds of light is essential to understanding the full, violent story of these stellar families. Amidst the gravitational chaos and wind-whipped nebulae, one of the most bizarre transformations can occur: the creation of a cosmic zombie. This isn't a reanimated corpse in the traditional sense, but a star that effectively cheats death by consuming its neighbor, emerging from a stellar merger looking and acting far younger than it truly is. The most dramatic version of this scenario starts with two stars in a perilously tight binary pair, spiraling closer and closer due to the relentless emission of gravitational waves. As their outer atmospheres finally touch, a fantastic and violent dance begins. Instead of a simple collision, the two stars can begin to merge, their cores swirling around each other inside a shared, turbulent envelope of gas. This common envelope phase is a stellar fever dream, a brief but incredibly energetic state where friction and tidal forces convert orbital energy into a tremendous amount of heat, causing the combined object to balloon outward into a gigantic, puffed-up star that glows with an intense, angry light. If the merger is successful, the result is what astronomers call a blue straggler. In a typical star cluster, the massive, hot blue stars burn out the fastest, leaving behind older, redder stars. A blue straggler is the cosmic anomaly that breaks this rule. A star that appears unnaturally blue, hot, and youthful, shining brightly in a neighborhood where all its peers have already aged into retirement. Its blue color and high temperature are dead giveaways of a recent, violent rejuvenation. It hasn't discovered some fountain of youth. It has quite literally cannibalized a companion, stealing its hydrogen fuel and mixing it into its own core. This fresh fuel reignites nuclear fusion with a new intensity, causing the star to shrink, heat up, and blaze with a borrowed brilliance. It's the stellar equivalent of a middle-aged person suddenly acquiring the metabolism and vitality of a teenager, all because they absorbed the life force of their sibling. The observational signatures of such an event are a forensic puzzle for astronomers. The first clue is often a sudden and sustained brightening in the star's light curve, a telltale sign of the merger event itself. This can be followed by a period of intense variability as the star struggles to find a new equilibrium, its outer layers churning violently. Spectrographic analysis reveals the chemical fingerprints of the crime. The atmosphere of a merger product will often show unusual chemical abundances, such as an overabundance of lithium, an element that is normally destroyed in a star's hot interior. This lithium is a relic from the cooler outer layers of the devoured companion, dredged up to the surface during the chaotic mixing of the merger. Furthermore, the star might show signs of rapid rotation. As the two stars merged, their combined angular momentum would have sent the new object spinning at a breakneck speed, much like a figure skater pulling in their arms during a spin. This rapid rotation can sometimes be so extreme that the star becomes oblate, bulging at its equator, and can even trigger powerful magnetic activity and starspots. This cosmic vampirism doesn't always result in a perfect merger. Sometimes the process is messier, leaving behind a strange, stripped-down object. Imagine a lower mass star being slowly consumed by a white dwarf, the dense Earth-sized core of a dead star. The white dwarf siphons material from its companion, but if the transfer rate is just right, it can ignite hydrogen fusion in a stable shell on its surface. This creates a super-soft X-ray source, an object that emits copious amounts of high-energy radiation not from its core, but from this external nuclear burning layer. It's a star that is, in a sense, being kept artificially alive by a constant drip feed of stellar plasma, a zombie powered by the body of another. The presence of such objects within a Decuple system is a clear indicator of the complex and often predatory relationships that define these stellar families, where the lines between life and death for a star become profoundly blurred. But what kind of worlds could possibly coalesce from such a turbulent cradle? The planetary systems that emerge within a Decuple family are nothing like the orderly, concentric circles of our own solar system. Instead, they are architectural marvels of cosmic compromise, with orbits and configurations so peculiar they once existed only in the realm of science fiction. Imagine a planet not orbiting a single, serene sun, but a tight binary pair, a place where two suns would trace intricate patterns across the sky, sometimes eclipsing each other, other times rising and setting together. This is the classic Tatooine world, a circumbinary planet that treats the dancing stellar duo as its combined gravitational anchor. For such a world to exist, it must find a precarious balance, orbiting far enough outside the chaos boundary where the competing tugs of the two stars average out into a single, stable pull. From the surface, the dance of the suns would create a day cycle of mesmerizing complexity. There would be single sunrises and double sunsets, moments of double shadows stretching in opposite directions, and perhaps even periods of perpetual daylight if one sun rose just as the other was setting. The very concept of a year would be tied to the binary pair's orbit around each other, a cycle completely divorced from the planet's own long journey around them both. The presence of a second, or even a third, distant stellar companion in the wider system adds another layer of profound strangeness to this already exotic environment. A planet might be happily orbiting its binary host when every few centuries a brilliant third star swings into its night sky, outshining all other stars and casting a pale, second shadow for decades or even centuries at a time. This isn't just a beautiful light show, it's a gravitational sledgehammer. The distant star's periodic approach would exert a gentle but persistent tug on the entire inner binary system, causing the planet's orbit to wobble or precess over long timescales. This can lead to extreme Milankovitch-like cycles on a scale we can barely comprehend. The planet's axial tilt, its orbital eccentricity, and the orientation of its orbit could all be slowly modulated by this distant puppeteer. A world that enjoys a stable, circular orbit for millennia might gradually be stretched into a highly elliptical path, bringing it scorchingly close to its twin suns at one extreme and flinging it into a deep freeze at the other. The climate on such a world wouldn't just have seasons, it would have super seasons, epochs of fire and ice lasting for thousands of years, driven by the rhythmic gravitational nudge of a far-off stellar god. The challenge for climate stability, and therefore for any potential life on these worlds, is monumental. On a circumbinary planet, the location of the habitable zone itself is not a fixed band but a wobbling ring. As the two stars orbit each other, the distance between them changes, which in turn alters the total amount of energy they radiate into space. The habitable zone pulses in and out with this stellar heartbeat. A planet that was perfectly positioned for liquid water when the stars were at their farthest apart might be baked into a desert when they swing close together. Life would have to be incredibly resilient, capable of hibernating through long periods of extreme heat or cold, or migrating across the planet to follow the shifting temperate bands. Furthermore, the complex gravitational environment makes it incredibly difficult for a planet to retain a stabilizing large moon. A moon's orbit around its host planet would be severely perturbed by the constant gravitational tides from the two suns, making it likely to be ejected or to crash into the planet within a relatively short astronomical timeframe. Without a large moon to steady its axial tilt, the planet's climate would be subject to wild, unpredictable swings, turning any potential ecosystem into a chaotic gamble against the cosmos. Yet, against all odds, the cosmos finds a way. An even more bizarre configuration might be the P-type planet, a world that makes a grand, sweeping orbit around the entire central gravitational mass of the Decuple system. From this distant vantage point, the 10 stars would appear as a single, brilliant cluster, a multifaceted jewel at the heart of its sky. The light on this world would be a blended, constant glow with no true night, only a dimming as different stars pass behind one another. Its year would be immense, lasting perhaps hundreds of thousands of Earth years, but its climate could paradoxically be far more stable than that of its inner system cousins. So far from the stellar fray, the individual gravitational tugs largely cancel out, and the blended starlight provides a relatively constant source of warmth. The greatest threat to such a world would not be daily fluctuations, but catastrophic, rare events, a sudden close encounter between two stars elsewhere in the system that sends gravitational shockwaves rippling outwards, potentially destabilizing the planet's orbit and casting it adrift into the interstellar dark. In a Decuple system, every planetary architecture is a testament to temporary stability snatched from the jaws of chaos, a fleeting experiment in cosmic order that may last for 1 billion years or be undone in a single stellar near miss. Now let's zoom out from the internal chaos of a single Decuple family to witness its colossal impact on the wider galactic neighborhood. A system of 10 massive stars isn't just a self-contained spectacle. It's a gravitational powerhouse that acts like a cosmic wrecking ball and a construction crew all at once, capable of reshaping the destiny of its entire host star cluster. Imagine a crowded stellar city, home to thousands or even millions of stars, all orbiting a common center. In such a dense environment, the introduction of a single, hypermassive object like a Decuple system fundamentally alters the gravitational landscape for everyone. Its immense collective mass creates a deep, localized gravity well, a kind of central traffic circle around which the other stars must now navigate. This doesn't just create a gentle ripple, it can completely rewrite the rulebook for how the cluster evolves over billions of years. The most direct effect is the gravitational disruption of nearby stellar orbits. Picture a star in the cluster going about its business on a stable, predictable path. When it drifts too close to the Decuple system, the complex, shifting gravitational pull from 10 different sources throws its trajectory into chaos. The star might receive a powerful gravitational slingshot, boosting its velocity and flinging it onto a new, highly elliptical orbit that takes it screaming through the cluster's core. In more extreme cases, the star can be ejected entirely, becoming a hypervelocity runaway that escapes the cluster's grip forever. This process, known as dynamical heating, gradually injects energy into the cluster. Over astronomical time, this relentless gravitational stirring can actually prevent the cluster from gravitationally collapsing in on itself, keeping it puffed up and diffused. The Decuple system acts like a persistent internal engine of chaos, its gravitational jolts counteracting the natural tendency for stars to sink toward the cluster's center, thereby helping to determine the entire cluster's final size and density profile. But the influence isn't always destructive. This same immense gravitational power can paradoxically act as a stabilizing force, a central anchor that helps bind the entire cluster together. In many clusters, the combined gravity of all the stars is barely enough to hold the system against the relentless tidal pulls of the galaxy itself. As the cluster orbits the galactic center, the difference in gravity between its near and far side, the galactic tide constantly tries to tear it apart. A massive Decuple system sitting near the cluster's core significantly deepens the cluster's overall gravitational potential well. This makes it much harder for stars on the outskirts to be stripped away by these external forces. It's like having a much heavier weight in the center of a sheet you're shaking. The edges might still flutter, but the center holds firm and more of the material stays in place. For some clusters, the presence of one or two of these stellar behemoths might be the critical factor that allows them to survive for billions of years instead of dissolving into the galactic field star population. Perhaps the most spectacular influence is the system's ability to trigger new waves of star formation in its vicinity. This isn't a gentle invitation, it's a violent shove. When a decuple system plows through a nearby molecular cloud, a cold, dark nebula of gas and dust, it does so with terrifying force. The system's collective radiation output, especially the intense ultraviolet light from its most massive O-type stars, bombards the cloud. This radiation heats and ionizes the gas, creating immense pressure that compresses the surrounding cold, neutral material. This process, known as radiative feedback, can squeeze pockets of the cloud past their point of gravitational stability, causing them to collapse under their own weight and ignite into new second-generation stars. It's a chain reaction of creation where the death of one gas cloud is directly caused by the decuple system, leading to the birth of an entire new stellar family nearby. The mechanical force of the system's colliding stellar winds adds another layer to this creative destruction. As we've seen, these winds create vast bubbles of million-degree gas that expand outward into space. When this expanding superstructure slams into a cold molecular cloud, it acts like a colossal snowplow. The shock front rams into the cloud, sweeping up the gas and dust into an incredibly dense, cold shell. Within this compressed shell, gravity can quickly take over, fragmenting the material into new protostellar cores. We see the brilliant evidence of this in nebulae like the Orion Nebula, where the fierce radiation and winds from the central trapezium cluster of massive stars are actively sculpting the gas and triggering the formation of a new generation of stars right on its doorstep. A decuple system would be this process on overdrive, its collective winds and radiation creating a far more powerful and complex trigger. The resulting baby stars would often be arranged in a beautiful spherical shell surrounding the system, a stellar echo of the immense shock wave that gave them life. This means that a single, chaotic family of 10 stars can serve as the catalyst for the birth of hundreds more, seeding its corner of the galaxy with new stellar systems for millennia to come. But beyond the brilliant light shows and gravitational hurricanes, some of these systems have been caught broadcasting on a completely different frequency, emitting powerful and erratic signals that have left astronomers utterly perplexed. It began with radio telescopes scanning the sky, their massive dishes tuned to listen to the faint whispers of the cosmos when they picked up a roar. Certain decuple systems were shining with an intense, crackling radio brilliance that flickered and flared in ways that defy all conventional explanations for stellar activity. A single, magnetically active star like our Sun does produce radio waves, but it's a faint, predictable hum. What we're detecting from these chaotic families is a full-throated, staticky scream, a signal so strong and variable that it points to something far more exotic and energetic happening within the stellar group. This isn't just a star making noise, it's the signature of a system-wide electromagnetic storm, a tangled web of magnetic forces being stretched, snapped, and reconfigured on a colossal scale. The leading theory to explain this radio cacophony centers on the violent interactions between the magnetic fields of the different stars. Every star has a magnetic field, a vast, invisible structure that extends far out into space. In a peaceful system, these fields exist in isolation, but in a decuple system, they are forced into uncomfortably close quarters. As the stars whip around each other on their complex paths, their magnetic fields don't just passively coexist, they slam into each other, twist around one another, and violently reconnect. Magnetic reconnection is one of the most energetic processes in the universe. It occurs when magnetic field lines with opposite directions are forced together, suddenly breaking and reconnecting in a new configuration. This releases a staggering amount of stored magnetic energy in an instant, accelerating charged particles to nearly the speed of light. These ultra-relativistic electrons then spiral along the newly formed magnetic field lines, emitting a broad, intense blast of radio waves as synchrotron radiation. It's a continuous celestial short circuit, a dance of titanic forces where the gravitational chaos outside the stars directly fuels an electromagnetic frenzy within the space between them. This magnetic mayhem can be dramatically amplified in systems containing specific types of stars, particularly close binaries where one star is a rapidly rotating red dwarf. These small, cool stars are notorious for their ferocious magnetic activity, capable of unleashing stellar flares that make our sun's largest eruptions look like tiny sparks. Now, imagine such a star locked in a tight orbit with another magnetically active star. As they orbit, their magnetic fields become coupled, tangling together like a ball of energized rubber bands. The constant orbital motion winds these fields up tighter and tighter, storing immense energy until, snap, a section of the field reconnects, triggering a superflare that dwarfs anything a single star could produce. These system-wide flares would light up the entire region in radio waves, creating the brilliant, unpredictable pulses that our telescopes detect. The entire Decuple system effectively becomes a unified electrical circuit, where the motion of the stars themselves acts as a giant dynamo, pumping energy into a shared magnetic reservoir that regularly and violently discharges. Another compelling, though more speculative, idea involves planets caught in this electromagnetic crossfire. We know planets can exist in these systems, and a gas giant like Jupiter has its own powerful magnetic field. If such a planet were orbiting very close to one of the stars in a tight binary pair, it could be interacting with the star's magnetic field in an extremely energetic way. The planet's magnetic field, moving rapidly through the star's much larger magnetosphere, could act like a generator, creating intense electrical currents that flow between the two bodies. This star-planet interaction is a bit like dragging a magnet through a coil of wire, but on a cosmic scale. These currents could then funnel charged particles down onto the star's atmosphere at its magnetic poles, creating brilliant, localized radio hotspots that flash with every orbital period of the planet. The variability of the radio signal in this case would be tied directly to the planet's orbit, providing a potential, albeit incredibly challenging, method to detect unseen worlds by their electromagnetic footprint amidst the stellar chaos. Perhaps the most thrilling possibility is that these radio signals are not coming from the living stars at all, but from the dead ones hiding amongst them. The source could be a pulsar, a rapidly spinning, city-sized neutron star that we haven't yet identified through its pulses in other wavelengths. Pulsars are nature's most precise lighthouses, beaming out narrow, powerful rays of radio waves that sweep across space with each rotation. In a Decuple system, the environment is so complex that identifying the steady, rapid pulse of a neutron star from the jumble of other variable signals is like trying to pick out a single, steady drumbeat in a room full of screaming, chaotic noise. Furthermore, if this neutron star is in a tight binary orbit, its signal can be dramatically altered. The radio beams can be scattered, absorbed, or Doppler shifted by the surrounding plasma and the orbital motion, making the pulsations appear erratic or even completely smeared out into a continuous, bright radio glow. The intense radio emissions we see could be the scattered, tangled remains of a perfectly regular pulsar signal, its cosmic timekeeping scrambled by the very environment it calls home. Unraveling this mystery requires a symphony of telescopes working in concert across the electromagnetic spectrum. When a radio flare is detected, astronomers immediately alert other observatories. They point X-ray telescopes at the system to see if the magnetic reconnection event is also heating plasma to millions of degrees. They check optical and ultraviolet telescopes to see if there is a corresponding brightening from a stellar superflare. By correlating these different signals, they can begin to isolate the cause. If the radio flare is accompanied by a huge outburst of X-rays and a bright optical flare, the culprit is likely magnetic reconnection between stars. If the radio emission is more steady and coincides with a specific periodic wobble in the system, a hidden pulsar becomes a stronger suspect. Each new observation adds a piece to the puzzle, slowly revealing whether we are witnessing the death throes of a stellar magnetosphere, the cries of a tormented planet, or the scrambled song of a cosmic zombie, its steady pulse lost in the stellar crowd. Out in the cosmic wilderness, some decuple systems stage a light show of such peculiar coordination that it seems almost orchestrated. This is the Christmas tree effect, a phenomenon where multiple stars within the same system flare up in a seemingly synchronized sequence, their brilliant outbursts twinkling across the darkness like lights on a celestial holiday tree. It's a form of stellar harmony that defies the expectation of random, isolated activity, suggesting a hidden connection between stars that are, by traditional standards, vast distances apart. The flares themselves are titanic explosions of magnetic energy, far more powerful than anything our sun produces, but it's their coordinated timing, their apparent conversation across the void, that transforms a chaotic system into a place of eerie, beautiful synchronicity. The most compelling explanation for this stellar chorus points to vast, interconnected magnetic fields that act as a cosmic wiring system. In a tightly packed decuple system, the magnetospheres of individual stars, the vast, invisible bubbles of their magnetic influence, may not remain isolated. Instead, they can stretch out and physically touch, tangling together to form a single, system-wide magnetic web. When a flare erupts on one star, it doesn't just release light and radiation. It sends a shock wave rippling through this shared magnetic structure. This shock wave, traveling along the magnetic field lines at a significant fraction of the speed of light, can almost instantly deliver a powerful jolt of energy to a neighboring star. Think of it like tapping one end of a taut net and watching the vibration travel instantly to the other side. This sudden, external agitation can destabilize the magnetic field of the second star, triggering it to release its own pent-up energy in a sympathetic flare. The result is a chain reaction, a domino effect of stellar fireworks where the flash of one star directly causes the flash of another, creating the illusion of a planned, rhythmic display. An alternative and equally fascinating mechanism involves a central, hyperactive object acting as the conductor for this cosmic orchestra. Many of these systems contain at least one star that is a magnetically volatile powerhouse, such as a rapidly spinning red dwarf prone to superflares or a neutron star with an immensely powerful magnetic field. This central object could be periodically bombarding its stellar siblings with intense bursts of radiation or high-energy particles. When this directed blast of energy slams into the atmosphere of another star in the system, it can act as a direct trigger. It's the astrophysical equivalent of holding a blowtorch to a balloon. The external pressure forces a sudden and violent release. The timing of the subsequent flares would then be locked to the rotation or flaring period of the central trigger star, creating a predictable, repeating pattern of illumination across the system. This would mean the other stars aren't flaring of their own accord, but are being forced to flare in response to the relentless bullying of their most energetic family member. For astronomers, observing and untangling this coordinated flaring presents an incredible challenge and a unique opportunity. The light curves from these events are a chaotic superposition of multiple overlapping bursts, a data stream that looks less like a clean signal and more like frantic static. To decode it, scientists use sophisticated statistical analyzers to hunt for correlations and time lags between the flares on different stars. They create computer models of the system's complex magnetic geometry. running simulations to see if a flare-on star A could realistically travel through the proposed magnetic web to trigger a flare on star B within the observed timeframe. The James Webb Space Telescope, with its ability to observe in the infrared, offers a new window into this phenomenon, potentially allowing researchers to see the heated regions on stellar surfaces where these magnetic connections are anchored, mapping the invisible circuitry that binds the stellar family together. The implications of this phenomenon reach far beyond a beautiful light show. The Christmas tree effect provides a living laboratory to study magnetic fields and flare physics under conditions impossible to replicate anywhere else. It demonstrates that stars in dense systems do not evolve in isolation. Their magnetic lives are intertwined, their most violent outbursts capable of influencing one another across vast distances. This interconnectedness has profound consequences for the potential habitability of any orbiting planets. A world might orbit a relatively quiet star, only to be periodically sterilized by a colossal flare triggered not by its own sun, but by a magnetic impulse from a noisy stellar neighbor light years away. It paints a picture of a decuple system as a single, electrically and magnetically integrated entity, where the fate of one star and any world it hosts is inextricably linked to the turbulent activity of all the others. We've seen how decuple systems can fling stars out into the void, but what if the tables were turned? What if the system itself was the one that had been stolen? Among the most astonishing discoveries is the evidence that some of these 10-star families are not native to the Milky Way at all. They are cosmic immigrants, survivors of a galactic massacre. Their unique, almost alien, chemical fingerprints and their peculiar paths through space suggest they were once the proud inhabitants of smaller dwarf galaxies that our own Milky Way devoured in the deep past. This isn't just a theory, it's a form of celestial archaeology where the stars themselves become fossils, telling the story of our galaxy's violent, cannibalistic history. To understand how we know this, you have to think about galactic chemistry. Stars formed in different environments cook up different blends of elements. Our Milky Way, a large and relatively evolved galaxy, has seen multiple generations of stars live die and seed its gas clouds with heavy elements like iron, oxygen, and silicon. This gives stars born in the Milky Way a specific chemical signature, a certain ratio of these elements that acts like a birth certificate. Now, when astronomers analyze the light from certain decuple systems, they find stars with a starkly different chemical makeup. They are often described as metal poor, meaning they possess far smaller amounts of these heavy elements compared to the typical Milky Way star. This poverty of metals is a dead giveaway. It indicates that these stars were born long ago in a much smaller, more primitive galaxy, a place where fewer generations of stars had lived and died to enrich the cosmic pantry with heavier elements. They are relics from an earlier, more pristine time in the universe, preserved by chance within their complex stellar family. The other piece of evidence is kinematic, meaning it relates to their motion. Stars native to the Milky Way's disk generally travel on orderly, circular orbits around the galactic center, like cars on a vast cosmic racetrack. But these suspicious decuple systems break all the rules. They often move on highly inclined, eccentric orbits, sometimes even going the wrong way, orbiting in a retrograde direction against the galaxy's dominant spin. When scientists use powerful computers to track these wild paths backward in time, they don't lead to a calm birthplace within the Milky Way's disk. Instead, they converge, pointing to a single, dramatic event, the accretion of a dwarf galaxy. Billions of years ago, a small satellite galaxy, pulled inexorably by the Milky Way's immense gravity, would have been stretched, shredded, and finally absorbed. Its stars were not destroyed but scattered, cast into these chaotic, looping orbits that remain as a permanent record of the disruption. The decuple system, with its strong internal gravity, managed to stay together during this cosmic dismemberment, a tight-knit family that survived the destruction of its original home. This discovery transforms our understanding of these systems from mere cosmic curiosities into living historical monuments. They are not just 10-star families, they are surviving fragments of lost galaxies, celestial time capsules that drifted into our midst. Their continued existence is a testament to the resilience of gravitational bonds. Even as the larger structure of their host dwarf galaxy was being torn apart by the Milky Way's tidal forces, the intense gravitational pull that bound these 10 stars together was enough to withstand the chaos. They held fast, a stable island in a sea of disruption, and were eventually adopted into the Milky Way's halo, a vast spherical cloud of old stars that surrounds our galaxy's main disk. Finding them there is like finding a distinct, ancient dialect still being spoken in a modern city. It's a direct, tangible link to a chapter of our galaxy's history that would otherwise be invisible. The implications of this galactic cannibalism extend far beyond a single system. Each one of these immigrant Decuple families serves as a crucial data point for astrophysicists trying to piece together the Milky Way's growth history. By studying their chemical compositions and orbits, we can estimate not just that a merger happened, but when it happened. Different dwarf galaxies consumed at different epochs leave behind distinct stellar populations. The presence of a particularly metal-poor Decuple system on a specific orbit might be the smoking gun for one of the Milky Way's most ancient meals, perhaps even the foundational merger that helped form our galaxy's halo in the first place. In this way, these complex stellar systems become more than just objects of study. They become dynamic tools for galactic forensics, helping us write the biography of our own cosmic home, one stolen family of stars at a time. And within that delicate orbital balance, we find one of the most profound puzzles in our search for life, the habitable zone conundrum. In a simple system like our own, the habitable zone is a relatively stable band around a single star, a region where the temperature is just right for liquid water to potentially exist on a planet's surface. It's often called the Goldilocks zone, not too hot, not too cold. But transplant that concept into a Decuple system, and the entire idea of a stable, life-friendly region shatters into 1,000 pieces. Here, the habitable zone isn't a placid, stationary ring. It's a pulsating, shifting, and wildly unpredictable volume of space that changes shape with the frantic rhythm of the stellar dance. A planet's potential for liquid water becomes a fleeting opportunity, a brief window that opens and closes as different stars dominate its sky and their combined light and heat wax and wane. Consider the journey of a single world locked in a stable orbit around one of the system's tight binary pairs. For part of its long year, the two stars in that pair might be close together, appearing in the sky as a single, brilliant, double-pointed sun. The total energy flooding the planet skyrockets, pushing its surface temperatures into a scorching extreme. Then, as the planet continues its orbit and the two stars swing to the opposite sides of their own dance, they appear widely separated in the sky. The total stellar flux plummets, and the world plunges into a deep freeze. This isn't a gentle seasonal change like our winter and summer. It's a radical oscillation between a boiling greenhouse and an icy wasteland, all dictated by the orbital period of the central binary, which could be a matter of days, weeks, or years. The very location of the habitable zone around that binary pair is constantly wobbling in and out, a moving target that the planet dips in and out of, never resting in the comfort zone for long. The complexity only deepens when you factor in the wider system. That same planet, while dealing with the light variations from its two immediate parent stars, also receives periodic contributions from the other 8 stellar members of the family. Imagine a scenario where, for a century, the planet's climate is governed by its binary suns. Then, a third, incredibly brilliant O-type star from the outer layers of the system makes its closest approach. For decades, this stellar giant dominates the night, shining with the intensity of 1,000 full moons and pouring enough additional ultraviolet radiation onto the planet to strip away atmospheres and boil off oceans. The concept of a habitable zone becomes almost meaningless in such a dynamic environment. It's not a single zone at all, but a series of overlapping, time-varying shells of possibility, each tied to the orbital period of a different star or pair of stars. A planet might be habitable for a few thousand years when the orbital configurations are just right, only to become sterile for the next 100,000 as the stellar symphony falls out of sync. This bizarre reality forces us to completely rethink what habitability even means. Life as we know it requires stability over geological timescales, hundreds of millions of years of relatively consistent conditions for evolution to work its slow magic. In a decuple system, that kind of long-term stability is the ultimate cosmic luxury. For life to gain a foothold, it would need to be incredibly resilient, capable of hibernating through eons of frozen darkness or burrowing deep underground to survive periods of intense surface heating and radiation. Alternatively, life might find a way in subsurface oceans, safe from the tempestuous skies, powered by geothermal vents rather than sunlight. The most likely candidate for a living world in such a system might not be a terrestrial planet at all, but a moon orbiting a gas giant, where tidal forces from the massive planet provide internal heat that is independent of the chaotic stellar energy from above. The search for biosignatures, the chemical signs of life, in these environments becomes a monumental challenge, as any atmosphere would be subjected to constant chemical bombardment from different wavelengths of starlight, making it difficult to distinguish the subtle signals of biology from the overwhelming noise of astrophysical processes. And so we come to a discovery that reveals the true architectural genius behind these stellar metropolises. It turns out the key to their survival isn't found in the chaotic interplay of 10 individual stars, but in a clever nesting of smaller, more stable families. Astronomers have uncovered that many decuple systems are not a free-for-all gravitational mosh pit, but are instead masterfully constructed from a series of triple-star subsystems. Imagine a sprawling city not built from individual houses, but from sturdy, self-contained neighborhoods. Each neighborhood has its own internal rules and stability, and it's the interaction between these stable neighborhoods that defines the city as a whole. That is the hierarchical secret to these cosmic giants. Within the apparent pandemonium, these triple systems form the fundamental building blocks. You will often find a tight trio of stars locked in a complex but stable dance at the very heart of the system. These are not just any three stars, they are arranged in a precise configuration that gravitational theorists call a hierarchical triple. In this setup, two stars form a tight inner binary, whipping around each other in a frantic close orbit. The third star then orbits this central pair at a much greater distance, effectively treating the binary as a single, combined gravitational object. This creates a miniature, stable solar system in its own right. The immense separation between the inner binary's orbit and the outer star's orbit is what provides the stability. The gravitational influences are cleanly separated, preventing the kind of close encounters that would lead to a catastrophic ejection. It's a gravitational structure that is remarkably robust, a tiny island of order within the greater sea of stellar chaos. This hierarchical principle doesn't stop with a single triple. The entire decuple system is essentially a pyramid of these stable structures. One of these triple subsystems itself can become a single gravitational unit. It can then orbit another triple subsystem, creating a new, larger binary system where each component is not a single star, but a trio of stars. This new 6-star unit can then, in turn, orbit another pair or triple, building up layer by hierarchical layer until the full 10-star family is assembled. The genius of this architecture is that it localizes the most violent gravitational interactions to the innermost, tightest orbits. The stars in the close binary are constantly tugging at each other, but their chaos is contained. The wider orbits which link these triples together experience a much smoother, more averaged gravitational pull, as if they were orbiting single, massive objects. This structure prevents the wild, unpredictable swings that would occur if all 10 stars were interacting with each other on equal footing. It's a brilliant cosmic strategy for managing complexity, creating stability through compartmentalization. The discovery of these triples within multiples was a watershed moment for theorists trying to model how such systems could possibly last for billions of years. Computer simulations had long shown that throwing 10 stars into a virtual box and letting gravity take over almost always resulted in a rapid disintegration. Stars would be flung out, others would collide, and the system would quickly simplify into a smaller, less chaotic arrangement. But when scientists programmed their simulations to start with pre-formed hierarchical triples, the results were dramatically different. These structured systems could withstand the test of time, their orbits oscillating and precessing but never crossing the line into true anarchy. The triple subsystems act as shock absorbers for the entire structure. When a gravitational disturbance from one part of the system ripples inward, it is often dampened and smoothed out by the stable dynamics of the triple it encounters, preventing a chain reaction of instability from cascading through the entire family. This prevalence of triple systems also provides a crucial clue to their formation. It suggests that these decuple families are not assembled by random captures later in life, a process that would be incredibly unlikely to produce such neat hierarchical structures. Instead, they must form this way from the very beginning. The current model points to a process called turbulent fragmentation. In the dense, chaotic core of a giant molecular cloud, the collapsing gas doesn't just split into 10 individual protostars. It first fragments into several smaller clusters. Within these clusters, the gas itself can fragment again, often naturally producing these stable triple systems as a preferred outcome of the complex interplay of gravity, rotation, and magnetic fields. These triple systems are then drawn together by their mutual gravity as the surrounding gas dissipates, settling into the layered, hierarchical architecture we observe today. They are born as a federation of stable triples, a structure that grants them the resilience to survive the tumultuous early phases of stellar life and persist as magnificent, long-lived cosmic families. Now, let's turn our attention to a phenomenon that uses the universe's most precise natural timekeepers to probe the deepest gravitational secrets of these systems. As we've seen, decuple systems are gravitational roller coasters, but some of them hide within their confines a pulsar, a rapidly spinning neutron star that beams radiation like a cosmic lighthouse with metronomic precision. These objects are so regular in their pulses that they rival atomic clocks, providing astronomers with an unparalleled tool for measuring the fabric of spacetime itself. Yet, when a pulsar finds itself entangled in a 10-star family, something strange happens to its impeccable rhythm. Its steady tick-tock-tick begins to stutter. The arrival times of its pulses become slightly early or frustratingly late, deviating from perfect prediction by mere milliseconds. These pulsar timing anomalies are not mere glitches. They are tiny whispers from the cosmos, hinting at hidden masses and warped space that we cannot see directly. The primary suspect for these timing irregularities is the immense and complex gravitational field generated by the system's many stars. According to Einstein's theory of general relativity, mass curves the fabric of spacetime. A pulsar's radio beam travels through this curved space on its way to us, and as the stars in the system move along their intricate orbits, the shape of this gravitational landscape is constantly changing. Imagine the pulsar's signal as a marble rolling across a vast, flexible trampoline that has 10 heavy bowling balls moving around on it. The path the marble takes, and thus the time its journey requires, will change depending on the precise positions of the bowling balls. When the stars align in a certain way, creating a deeper gravitational well along our line of sight, the pulsar's signal has to climb out of a steeper hill, causing a slight delay. When the geometry is different, the path might be shorter, making the pulse arrive a tiny bit early. This effect, known as the Shapiro time delay, is a direct probe of the warped spacetime within the system, and in a decuple environment, the variations are magnified and compounded in a way that is unique in the known universe. But the gravitational pull of the visible stars alone may not account for all of the strange timing shifts. Another tantalizing possibility is that these rhythmic hiccups are caused by the presence of unseen planets orbiting the pulsar itself. The idea of a planet surviving the supernova explosion that created the neutron star is incredible but not impossible. A world could have been flung into a wide orbit during the cataclysm, or it could be a second-generation planet formed from the debris of the destroyed companion star. As this hidden planet orbits the pulsar, it tugs its parent star back and forth. When the planet pulls the pulsar slightly toward us, the next pulse in the sequence has a shorter distance to travel and arrives early. When the planet pulls the pulsar away, the pulse has to travel farther and arrives late. By meticulously mapping these periodic delays over years, astronomers can, in theory, detect the planet's presence, measure its mass, and even determine its orbit, all from the subtle irregularities in a clockwork signal from thousands of light years away. It would be the ultimate demonstration of indirect detection, finding a dark world by the shiver it imposes on the most precise timepiece in the galaxy. Perhaps the most mind-bending explanation for these anomalies involves physics beyond our current understanding of gravity. The extreme gravitational environment of a decuple system, with its rapidly changing and intense fields, is a perfect laboratory for testing the limits of Einstein's theory. The timing residuals, the small, unexplained differences between the predicted and actual pulse arrival times, could be a signature of exotic phenomena. One possibility is that we are seeing the faint imprint of gravitational waves rippling through the system. Not the high-frequency waves from merging black holes, but a persistent, low-frequency gravitational wave background generated by the orbital motion of the system's most massive binaries. These waves would minutely stretch and compress spacetime along the path of the pulsar's signal, creating a correlated pattern of timing deviations. Alternatively, the anomalies could point toward more speculative ideas, like the influence of a cloud of dark matter particles gravitationally bound to the system, whose subtle collective pull subtly alters the pulsar's timing in a way that normal matter cannot explain. Decoding this pulsar Morse code requires a global effort. Projects like the International Pulsar Timing Array combine data from the world's most powerful radio telescopes, creating a galaxy-spanning observatory that is exquisitely sensitive to these tiny temporal distortions. By monitoring an entire network of millisecond pulsars, both within and outside of complex systems, astronomers can cross-reference the timing anomalies. If a deviation is seen in only one pulsar, it likely points to a local cause, like an orbiting planet or a passing star within its own system. But if a correlated signal is found across many pulsars across the sky, it could be the first direct evidence of a background hum of gravitational waves, a discovery that would open an entirely new window on the universe. The strange, stuttering heartbeat of a pulsar lost in a crowd of stars is more than just a curiosity. It is a sensitive probe, a natural instrument that allows us to weigh the invisible, map the warped, and perhaps one day hear the faint ripple of spacetime itself. For all their internal complexity and hierarchical stability, decuple systems are not isolated fortresses in space. They travel on vast orbits around the galactic center, and on their multi-million-year journeys, they occasionally cross paths with other massive objects. This brings us to a discovery that highlights their profound vulnerability, the flyby catastrophe scenario. Researchers running sophisticated gravitational simulations have found that a close encounter with something as simple as a wandering star, or something as colossal as a giant molecular cloud, can act like a cosmic cue ball, striking the delicate architecture of a 10-star family and sending it into a cascade of chaos from which it may never recover. The stability of these systems, it turns out, is a fragile illusion, perpetually one random encounter away from being shattered. The mechanics of such a flyby are deceptively simple in principle but devastating in their execution. The primary danger comes from tidal forces. When another massive object passes near the Decuple system, it doesn't pull on the entire family uniformly. The gravitational pull is stronger on the side of the system closest to the intruder and weaker on the far side. This difference in force creates a stretching effect, a tidal pull that tries to rip the system apart. Imagine holding a snowball by two ends and pulling. It doesn't just move, it deforms and begins to crumble. In a gravitational flyby, this tidal force doesn't just stretch the system momentarily. It injects a massive amount of energy into the stellar orbits, effectively giving the entire structure a violent, collective shake. Stars on the outer layers of the system's hierarchy, which are already the most loosely bound, receive the biggest jolt. Their orbits can be dramatically altered, stretched into long, looping paths that take them far from the core, or given so much energy that they achieve escape velocity, becoming the latest additions to the galaxy's population of rogue stars. What makes these events so catastrophic is the chain reaction they can trigger within the system's intricate gravitational web. A simulation might start with a solitary, sun-like star passing within a half-light year of a stable Decuple system, a seemingly safe distance by cosmic standards. The initial effect is subtle. The orbits of the outermost triple system begin to wobble and become more eccentric. But this is just the beginning. That now unstable triple subsystem, as it swings back into the inner core of the system on its new, perturbed path, acts as a gravitational wrecking ball. Its close passage disrupts the next layer of the hierarchy, perhaps tightening one inner binary to a dangerous degree while widening another. This second-order disruption then ripples inward, affecting the tightest, most fundamental pairs. In a matter of a few orbital periods, which could be just centuries or millennia in astronomical time, the entire carefully balanced hierarchy can be undone. A system that has existed for 1 billion years can be permanently transformed in a cosmic blink. Some of the most dramatic outcomes of these flybys involve direct stellar collisions. In a stable Decuple system, the hierarchical orbits are designed to keep stars at a safe distance from one another, but a powerful gravitational perturbation can throw this caution to the wind. Simulations show that a flyby can drastically alter the orbital angular momentum of an inner binary, sending its two stars on a radical new path that drives them directly into each other. Unlike the slow, graceful merger driven by gravitational waves, this is a sudden, violent impact. When two main sequence stars collide, they don't simply bounce or shatter. They merge into a single, monstrously large star, a blue straggler on steroids, flooded with fresh hydrogen that ignites a ferocious new phase of nuclear burning. The collision releases an immense amount of energy in a brilliant flash of light, outshining the rest of the system combined for a brief period. This new, overmassive star is then doomed to a short, spectacular life, likely ending in a supernova that will deliver yet another gravitational shock to its already reeling stellar family. Another frequent result seen in these simulations is the creation of hypervelocity binaries. We've discussed single stars being ejected, but a flyby can be so precisely disruptive that it flings an entire bound pair out of the system. The intruder's gravity can give a tight binary pair just the right combination of velocity and direction to escape the collective pull of their 8 siblings. This means two stars, still orbiting each other frantically, are sent racing into interstellar space as a paired unit. We have observational evidence that such objects exist. They are binary systems moving at speeds far too high to be bound to the galaxy's disk, their trajectories pointing back to dense stellar environments where such gravitational slingshots are possible. The Decuple system, in losing this binary, has not just been simplified. It has actively seeded the galaxy with a new, fast-moving celestial object, a double star on a lonely journey through the galactic halo. The aftermath of a flyby is rarely a clean dissolution. More often, it leaves behind a system that is profoundly reshuffled, a shadow of its former self. The new configuration might be a stable sextuple or septuple system, having lost 3 or 4 of its original members to ejection. The remaining stars settle into a new, simpler hierarchy, one that might be stable for another billion years, or might be teetering on the edge of collapse, ready for the next minor perturbation to finish the job. The once orderly structure is gone, replaced by a system that bears the scars of the encounter. Astronomers can sometimes spot these survivors by their unusual dynamic stars on highly inclined orbits relative to the rest, or a distinct lack of members in what should be the outer layers of the hierarchy, like a tree that has lost all its outer branches in a storm. These systems are the living proof that the cosmos is a dynamic and sometimes violent place, where even the most magnificent and complex structures are subject to the random whims of a passing celestial giant. Yet another layer of cosmic mystery emerges when we focus our attention on one of the most baffling phenomena in modern astronomy, the fast radio burst. These are not gentle signals, they are unimaginably powerful, millisecond-long blasts of radio waves that flash across the cosmos, often releasing more energy in that split second than our Sun does in 80 years. For a long time, their origins were completely unknown, cosmic ghost signals appearing at random points in the sky. Then, astronomers made a crucial breakthrough. They found that some of these bursts repeat. And when they traced the location of a few of these repeating FRBs, they didn't lead to isolated, quiet regions of space. Instead, they pointed back to incredibly dynamic and crowded stellar environments, including galaxies with a high density of star clusters and, by extension, a high likelihood of containing complex, high multiplicity star systems like our Decuple families. This has led to a highly speculative but electrifying hypothesis. Could the very same magnetic mayhem that lights up Decuple systems in radiostatic also be capable of producing these titanic, universe-spanning shrieks? The key to this radical idea lies in the sheer scale of the magnetic forces at play. We've already seen how the tangled magnetic fields of 10 closely orbiting stars can create a continuous crackle of radio emission through reconnection events and flares. But what if the conditions were just right for a magnetic cataclysm of an entirely different magnitude? Imagine one of the system's most volatile stars, like a magnetar, a neutron star with a magnetic field so impossibly strong it defies comprehension, a quadrillion times more powerful than Earth. If such an object were present in a Decuple system, its own immense field would be constantly stressed and twisted by the gravitational tides and the magnetic fields of its 9 stellar companions. This external agitation could act as a trigger, causing a starquake on the magnetar's solid, crystalline crust. This isn't a gentle tremor, it's a stellar-scale earthquake that violently shears the magnetar's crust, releasing a cataclysmic amount of energy and instantly reconfiguring its magnetic field lines in a single, catastrophic snap. The resulting magnetic reconnection event would be unlike any ordinary stellar flare. It would be a detonation, launching a blast of energy and a cloud of magnetized plasma that could generate the telltale, fleeting, and incredibly bright radio pulse we observe as a fast radio burst. But the story doesn't end with a single, unstable star. The Decuple system's complex gravitational dance itself could be the ultimate trigger. Consider a scenario where a magnetar is locked in a tight, eccentric orbit with another massive star. As the two swing perilously close at periastron, the point of their closest approach, the gravitational pull on the magnetar becomes immense. This tidal force could be the final straw, stressing the neutron star's crust beyond its breaking point and inducing a massive starquake that powers an FRB. The repeating nature of some bursts could then be explained by this orbital cycle. Every time the stars reach that critical point of closest approach, the same gravitational trigger is pulled, leading to another rupture and another brilliant radio scream. This would make the FRB a periodic, predictable event, its repetition schedule locked to the orbital clock of the binary pair within the larger stellar family. An even more exotic possibility involves the entire system's interconnected magnetic web. If the magnetic fields of several stars are truly linked, it's conceivable that a superflare on one star could, almost instantaneously, inject a colossal wave of energy into the magnetosphere of the magnetar. This external energy dump could force a global restructuring of the magnetar's own field, a process that would release a tremendous burst of radio waves as the field reconnects and reorders itself. In this model, the FRB isn't just about the magnetar alone, it's a system-wide event. The flare from a distant, seemingly ordinary star acts as the finger that pulls the trigger on a cosmic cannon, with the magnetar serving as the loaded gun. This would create a direct, albeit complex, link between stellar activity we can observe in other wavelengths and the sudden, mysterious appearance of an FRB. Of course, this hypothesis is met with healthy skepticism, as any good frontier science should be. The primary counter-argument is one of energy. While the magnetic reconnection events within a Decuple system are powerful, generating the focused, coherent energy required for an FRB that can be detected across billions of light-years is a tremendous leap. Some theorists argue that only the most extreme magnetic objects in the universe, like newly born magnetars or the aftermath of a neutron star merger, are capable of such an feat. Furthermore, the radio signals we directly observe from Decuple systems are a persistent, chaotic crackle, not the clean, millisecond spike of a classic FRB. Proponents of the link counter that we may simply be observing the difference between the small-scale, continuous reconnection that creates the radio noise and the rare, perfect storm of conditions that leads to a single, monstrous reconnection event capable of focusing a significant fraction of the system's total magnetic energy into a narrow, brilliant beam for a fraction of a second. The search for evidence to support or refute this idea is driving astronomers to use the most advanced tools at their disposal. When a new repeating FRB is discovered, one of the first priorities is to obtain a deep, multi-wavelength image of its host environment. Are there signs of a dense star cluster or a recent episode of violent star formation that could host these complex systems? The next step is to look for a counterpart, a flash of light or X-rays that coincides with the radio burst. If a magnetar in a Decuple system is the source, a massive starquake should also produce a brief but detectable flash of high-energy radiation. Observatories like the Chandra X-ray Observatory and the Swift satellite are constantly on alert, ready to swing into action when a new FRB is detected, hunting for that telltale X-ray signature that would confirm a magnetar's involvement. Finding such a counterpart would be the smoking gun, directly linking one of the universe's most powerful explosions to the turbulent, magnetic heart of a family of 10 stars. Until then, the connection remains one of the most compelling and strange possibilities on the frontier of astrophysics. A tantalizing hint that the greatest cosmic mysteries may be hidden not in the empty voids, but in the most crowded and chaotic stellar neighborhoods imaginable. Now we step into the realm of cosmic detective work so subtle it relies on shadows within shadows. It's called the shadow method, but you might know it as the transit method, a powerful tool turned nearly impossible inside a Decuple star system. The basic principle sounds simple enough. When a planet passes directly in front of its host star from our vantage point, it blocks a tiny fraction of the star's light, causing a brief, telltale dip in brightness. In a quiet system with one star, that dip is a clear, repeating signature. But place that same planet into a system with 9 other brilliant suns, and its faint shadow is utterly drowned in a sea of competing light. The background starlight is never constant. It's a chaotic, shimmering glare as the other stars orbit, eclipse each other, and flare, turning the entire sky into a flickering disco ball that completely obscures the tiny, whispering transit of a world. The challenge becomes a monumental exercise in signal processing. Astronomers aren't just looking for a needle in a haystack, they're trying to find a specific piece of dust on a single needle in a vast, shifting, and constantly rearranging haystack. The first and greatest hurdle is simply identifying which of the 10 stars the planet is actually orbiting. A single, small dip in the system's combined light could mean a planet transiting star A, or it could mean that star B has momentarily eclipsed a small, dim spot on star C. To have any hope, scientists must first create a near-perfect model of the system's complex stellar dance. They use years of data to chart every eclipse, every wobble, and every flare from all 10 stars, building a digital simulation of the system's light that accounts for every stellar phenomenon. Only once they can perfectly predict and subtract this overwhelming stellar cacophony from the observed light curve are they left with the residual signal, the quiet noise where a planet's shadow might be hiding. Success in this daunting task requires a specific and rare planetary alignment. The planet's orbit must be edge-on from our perspective, and it must be transiting a star that is itself relatively isolated in the system at that moment, not being blurred by the light of a close companion. The most promising candidates are planets orbiting a star in a very wide binary pair, where the two stars are so far apart they can be easily resolved and their light separated. Even then, confirming a shadow is a statistical battle. A single dip is meaningless, it could be noise. Astronomers must wait for that dip to repeat with perfect clockwork regularity, again and again over many years. They stack the data from each potential transit on top of each other, looking for that faint, repeating whisper to emerge from the random static. It's a test of patience and precision that pushes our observational capabilities to their absolute limit. Yet, against all odds, this method has scored some incredible victories. The most spectacular successes haven't been from finding Earth-sized worlds, but from detecting true giants, planets the size of Jupiter or even larger, orbiting very close to their host stars. These hot Jupiters create the deepest transits, blocking a more significant fraction of their star's light and producing a stronger signal that can just barely punch through the stellar noise. Finding one of these behemoths in a Decuple system was a thunderous confirmation that planet formation is not just possible in these extreme environments, but can produce startling outcomes. These are not gentle giants in wide orbits. They are scorched, monstrous worlds, likely forged in the outer reaches of the system, and then violently thrust inward by gravitational encounters, ending up in orbits so tight their years last only a few Earth days. The implications of this shadow hunting technique reach far beyond mere cataloging. Each successful detection provides a crucial data point for understanding how planetary systems assemble and survive within gravitational chaos. The very existence of a close-in gas giant implies a surprisingly stable disk during the system's early years, or a dramatic history of planetary migration driven by interactions with other stellar siblings. Furthermore, by measuring the depth and duration of the transit, astronomers can determine the planet's physical size relative to its star. If they can also measure the star's mass through its gravitational wobble, a Herculean task in itself within a 10-star system, they can calculate the planet's density. This simple number unlocks worlds of information, telling us if we're looking at a puffy, low-density gas giant or a dense, rocky super-Earth, offering a first glimpse into the nature of a world living under 10 suns. Every faint shadow captured is a direct window into the resilience of cosmic architecture, proving that even in the most tumultuous stellar families, planets can not only form but can also announce their presence to those patient enough to read the light. This brings us to a laboratory of unimaginable scale and precision, a place where Einstein's theory of general relativity faces its ultimate trial. While we can test the theory with some success in our relatively quiet solar system, a Decuple star system offers a crucible of gravitational extremes that no particle accelerator on Earth could ever hope to replicate. Here, the fabric of space-time isn't just gently curved, It is violently warped, twisted, and stirred by the combined mass and rapid motion of 10 stellar bodies, creating a dynamic environment where the more subtle predictions of relativity are amplified from faint whispers into measurable shouts. One of the most profound effects is the precession of orbits. In our solar system, Mercury's orbit slowly precesses, its elliptical path rotating around the Sun like a spirograph drawing. This is a key validation of general relativity, but the effect is tiny. In a decuple system, this phenomenon is magnified to an incredible degree. Imagine a tight binary pair of stars whipping around each other at a significant fraction of the speed of light. According to Newtonian gravity, their orbit should be a perfect, repeating ellipse. But Einstein tells us that the immense mass of these stars creates a deep well in spacetime, and as they move, they drag this well with them. The result is that the point of closest approach in their orbit, the periastron, doesn't stay fixed. It advances or precesses at a rate that can be thousands of times faster than Mercury's. In some simulated systems, the entire ellipse can make a complete rotation in just a few decades, a stark, observable deviation from the simpler laws of Newton that would be immediately apparent to any observer tracking their positions over time. The opportunities for testing relativity multiply exponentially when you add more stars to the dance. Consider a hierarchical triple where a distant third star orbits an inner binary. The precession of the inner binary's orbit itself begins to precess due to the gravitational influence of the outer star, an effect known as precession of the precession. This creates a complex, multi-layered gyroscopic motion that is exquisitely sensitive to the precise equations governing gravity. If general relativity is correct, the motions will match the predictions of its complex mathematics with stunning accuracy. But if there is even a tiny deviation, a slight mismatch in how mass and energy curve spacetime that isn't accounted for by Einstein's theory, it would show up as a growing discrepancy in the observed orbits over time. These systems act as nature's most sensitive interferometer, constantly measuring the validity of our fundamental understanding of gravity with every passing orbit. Beyond the slow drift of orbits, the system creates a natural spectacle of gravitational lensing on a staggering scale. We're familiar with the concept of a single massive object like a galaxy bending the light from a more distant quasar. Now picture 10 such lenses all moving. As the stars in a decuple system orbit, they continuously change the configuration of this gravitational lens array. A distant background star, whose light would normally travel in a straight line to us, has its path bent and distorted as it passes through this evolving maze of spacetime curvature. The result is not a single, steady Einstein ring, but a flickering, multiplexed mirage. The background star might appear to split into multiple, shimmering images that change in brightness and position, dancing around the edges of the stellar family in a complex, predictable yet chaotic ballet. By meticulously tracking this celestial light show, astronomers can literally map the gravitational potential of the entire system. They can weigh each star with incredible precision and even probe the distribution of any invisible dark matter that might be clinging to the system, using the bent paths of photons as their guide. Perhaps the most elusive relativistic effect to measure is frame dragging, also known as the lens-thirring effect. This is the idea that a massive, rotating object doesn't just warp the space around it, but actually drags that spacetime around with it, like a spinning ball submerged in a thick fluid. Our planet Earth produces a minuscule frame dragging effect, which has been painstakingly measured by satellites like Gravity Probe B. But in a decuple system, you have multiple, incredibly dense and rapidly spinning neutron stars or white dwarfs. As these stellar remnants whirl through the system, their immense rotation grabs the fabric of spacetime itself and twists it into a vortex around them. This has a direct, observable consequence. It causes the orbits of any nearby companions to slowly tilt. the entire orbital plane of a star orbiting a spinning neutron star will begin to wobble or precess in a direction perpendicular to the pull of gravity alone. Detecting this within a decuple system would be the holy grail of experimental relativity. It would require tracking the orbital inclination of a star with microscopic precision over many years, but the payoff would be monumental. A confirmed detection of strong frame dragging in a natural setting would provide the most direct evidence yet that space-time is not a static stage but a dynamic, malleable entity that can be set into motion by mass and spin. It would prove that the universe truly behaves as Einstein's equations describe, even under the most extreme conditions imaginable. These stellar families, in their relentless and complex motion, are not just cosmic curiosities. They are the ultimate proving grounds for the laws that govern the very structure of reality, offering tests of fundamental physics that we could never hope to construct in any laboratory on Earth. We now come to a discovery that ties the existence of these stellar giants to the most chaotic and powerful region of our galaxy. Far from being scattered randomly across the Milky Way, a surprising and disproportionate number of candidate decuple systems appear to be concentrated in a single, terrifyingly energetic place, the galactic center. This region, surrounding the supermassive black hole known as Sagittarius A, is a cosmic pressure cooker unlike any other, a maelstrom where the very conditions that can forge a 10-star family are the same forces that can tear one apart in an astronomical heartbeat. The immense gravitational tides and the sheer, crushing density of stars in this environment create a laboratory for stellar dynamics operating at its most extreme, where the rules of engagement for celestial bodies are rewritten on a scale of epic proportions. To understand why this area is such a fertile breeding ground, you must first grasp the sheer density of the stellar population there. While in our galactic suburb, stars are typically several light-years apart, the galactic center crams millions of stars into a region just a few dozen light-years across. It's the difference between a handful of people scattered across a vast field and a packed, roaring stadium. In this stellar metropolis, close encounters are not rare events. They are a constant, fundamental part of existence. Stars don't simply drift past one another. They frequently undergo gravitational interactions that can violently alter their destinies. It is within this frantic gravitational dance that the building blocks of decuple systems are forged. The prevailing theory, known as the capture model, suggests that in this environment, smaller, pre-existing star systems like triple or quadruple systems are constantly being thrown together. When two such systems pass close enough, their mutual gravity can bind them, not in a destructive collision, but in a new, stable hierarchical orbit. The overwhelming gravity of the surrounding stellar crowd acts as a kind of cosmic glue, sapping away the excess energy from the encounter and allowing the new, more complex family to form. It's a process of aggressive, forced mergers where the galactic center's chaos provides the perfect conditions for building stellar families of staggering complexity. Yet, for all its creative potential, the galactic center is an even more efficient destroyer. The same incredible density that fosters these forced unions also subjects them to relentless gravitational harassment. The most destructive force is not the supermassive black hole itself, but the extreme tidal forces it generates. A tidal force is the difference in gravity across an object. It's what causes ocean tides on Earth, but near Sagittarius A, this effect is magnified to a terrifying degree. As a decuple system orbits the black hole, the side of the system closest to the black hole feels a much stronger pull than the far side. This difference stretches the entire system, not just once, but continuously, like pulling repeatedly on a ball of putty. For a system whose stability relies on delicate hierarchical orbits, this constant tidal pulling is a death sentence. It injects energy into the outer layers of the system, gently but persistently prying stars loose. Over time, this process, known as tidal stripping, can evaporate the system from the outside in, shedding its outermost stars until only a tight, hardened core remains. The environment presents another, more immediate threat, the gravitational slingshot. The crowded conditions mean that a decuple system will inevitably have a very close encounter with another massive object, perhaps another large star cluster or even a lone, intermediate mass black hole. When this happens, the intruder's gravity can act as a powerful and precise catapult. A star on the outskirts of the decuple system can receive a tremendous gravitational kick, accelerating it to such a high velocity that it breaks free from its family's gravitational bonds forever. In some cases, the entire system can be sent careening on a new, highly elliptical orbit that takes it plunging through even denser regions of the galactic core, ensuring its eventual complete disintegration. The lifespan of a decuple system in this neighborhood is therefore not measured in billions of years, but perhaps in only millions. They are brilliant, temporary flowers blooming in a cosmic hurricane, their beauty and complexity destined to be short-lived. This connection to the galactic center profoundly changes our perspective on these systems. They are not the serene, long-lived patriarchs of quiet galactic regions, but rather the transient, spectacular products of the universe's most violent urban environments. Their prevalence there suggests that the formation of high-multiplicity systems might be a natural, common outcome in the densest stellar nurseries the universe has to offer. This insight allows astronomers to use the galactic center as a natural laboratory. By observing the demographics of these systems, how many there are, their distribution, and their various stages of disintegration, scientists can test sophisticated computer models of stellar dynamics under the most extreme conditions. Each candidate decuple system found in this maelstrom is a data point that helps refine our understanding of how gravity builds and breaks apart complex structures, offering a unique window into the violent heart of our own galaxy and the forces that have shaped its central stellar population for billions of years. But for all their intricate stability and hierarchical genius, these stellar metropolises are not eternal. They are temporary constellations in the grand timeline of the galaxy, destined for a spectacular and final unraveling. The very gravitational forces that sculpted their complex dance will ultimately be the instrument of their demise. This decay begins not with a bang, but with a slow, relentless whisper, the emission of gravitational waves. Every tight binary pair within the system as it orbits is constantly radiating away tiny amounts of energy in the form of these space-time ripples. This loss of energy causes the stars to spiral inward, drawing closer together with each passing millennium. It's an inescapable process, a gradual leak in the system's orbital energy that, over billions of years, fundamentally reshapes its internal architecture. The tightest pairs become progressively tighter, their orbits shrinking until the stars are practically touching, poised on the brink of a cosmic merger that will dramatically alter the system's balance of power. This slow-motion decay sets the stage for the system's most dramatic final acts, stellar collisions and cataclysmic explosions. As gravitational waves drive binary pairs closer, the chance of a direct impact skyrockets. Imagine two massive stars, their outer atmospheres already mingling, finally losing their last vestige of orbital momentum and plowing into one another. The result is not a simple merger but a titanic conflagration. The collision releases an immense burst of light, outshining the entire system for a brief, glorious period. The product is often a single, monstrously large star, a blue straggler of incredible mass, now flooded with fresh fuel but doomed to a short, furious life. This new stellar behemoth will burn through its nuclear fuel at a prodigious rate, living fast and dying young in a supernova explosion that will, in turn, rock the remaining stars with a powerful blast wave and a searing flash of radiation. Supernova become the system's primary mechanism for both destruction and transformation. When a massive star, whether born that way or created through a merger, exhausts its fuel, its core collapses. The resulting supernova is one of the most energetic events in the universe, and in a crowded decuple system, its effects are magnified. the blast wave can violently compress the atmospheres of nearby stellar siblings, potentially triggering new, albeit short-lived, episodes of star formation right within the family. More often, however, it delivers a devastating gravitational shock. The supernova explosion is almost never perfectly symmetrical. The dying star gives a powerful kick to the newly formed neutron star at its core. If this kick is too strong, the neutron star can be ejected from the system entirely, rocketing away as a lone pulsar into the galactic void. Even if it remains, the sudden loss of a significant fraction of the system's mass can be catastrophic. The delicate gravitational balance, painstakingly maintained for eons, is instantly shattered. Orbits that were once stable become wildly eccentric or simply unbound as the stars readjust to a new, lighter gravitational center. Through this cascading series of mergers and explosions, the system's population begins to dwindle. Stars are either consumed in collisions, blasted away by supernova kicks, or gently evaporated through gradual gravitational interactions. The once teeming family of 10 starts to shrink. A system might be reduced to a sextet, then a tight quartet, and finally, a lone, stable binary pair orbiting a common center of mass. But even this final pair is not safe. If it consists of two stellar remnants like neutron stars or black holes, their fate is sealed by the relentless pull of gravitational waves. They will continue their slow, inward spiral for eons, their orbital period shortening from years to days, then to hours, and finally to a fraction of a second before they collide in a final, universe-shaking event. Such a merger of two neutron stars creates a kilonova, a furnace where the heaviest elements in the cosmos, like gold and platinum, are forged and scattered into the surrounding nebula, a final chemical legacy of the system's violent end. The ultimate fate for many of these systems is not a single grand explosion, but a quiet dissolution. The gravitational bonds that once held the family together are gradually loosened by both internal decay and external perturbations. A close pass by a giant molecular cloud or another star cluster can provide the final nudge, injecting just enough energy to overcome the system's weakening gravity. One by one, the remaining stars are stripped away, their shared motion dissipating as they drift apart. They become individual field stars, joining the vast, anonymous population of the galactic disk or halo. Their tumultuous pasts as members of a decuple system would be hidden, betrayed only perhaps by their unusual chemical compositions or high velocities, subtle clues for future astronomers to decipher. What remains after the fireworks have faded and the stars have scattered is a ghostly legacy of exotic remnants. The most likely end product is a binary black hole system, two dark, silent sentinels of incredible mass, orbiting each other in the emptiness that was once a thriving stellar metropolis. Their formation story is written in the chaos that preceded them. They are the dense, dark cinders of massive stars that merged, exploded, and were refined through countless gravitational interactions. This binary black hole will continue to radiate gravitational waves, its orbit slowly decaying until, billions of years from now, it too will merge in an event that will briefly outshine a galaxy, sending a final, powerful ripple through the fabric of space-time. The Decuple system's incredible journey from a chaotic birth in a dense cloud to a stable, hierarchical family, and finally to a dispersed collection of remnants and lone stars, is a microcosm of the galactic life cycle. It demonstrates that even the most complex and seemingly permanent structures in the universe are merely temporary patterns in an endless cosmic dance of creation and destruction, their passing leaving behind only enriched space and the faint, ringing memory of gravity. So what have we truly learned from these 30 strange discoveries about decuple star systems? They are far more than a cosmic oddity. They are a profound challenge, a systematic dismantling of our long-held assumptions about how the universe is built. Every single discovery, from the gravitational wave factories and the rogue star foundries to the stellar zombies and the chaotic planetary architectures, points to one inescapable conclusion. The cosmos is not a place of serene, solitary suns and orderly orbits. It is a dynamic, turbulent, and deeply interconnected arena where the very processes of star and planet formation are pushed to their absolute limits. We conceived of planets forming in quiet, dusty disks, only to find them surviving in gravitational maelstroms where 10 suns light the sky. We thought we understood stellar life cycles, only to watch stars steal mass, reset their clocks, and merge into new beings entirely. The existence of these systems forces us to rewrite the textbooks, acknowledging that chaos and complexity are not the exception in our galaxy, but a fundamental part of its creative engine. These discoveries reveal a universe that is stunningly interconnected on every level. It's not just that 10 stars are gravitationally bound, it's that their fates are woven together through invisible magnetic webs, shared chemical histories, and relentless tidal forces. A flare on one star can trigger an eruption on another light years away. The death of a single stellar sibling in a supernova can scar the survivors and pollute them with the elements of its demise. These systems don't just exist in isolation, they actively shape their surroundings, ejecting runaway stars to travel the galaxy, triggering new waves of star formation with their fierce radiation, and potentially even broadcasting their existence through enigmatic signals like fast radio bursts. This interconnectedness blurs the lines between individual celestial objects, presenting a cosmos where a star's evolution, a planet's climate, and even the potential for life are dictated by the complex collective behavior of an entire stellar family. Ultimately, the journey through these 30 findings is a powerful lesson in cosmic humility and boundless curiosity. It teaches us that for every rule we think we've established, the universe has an exception waiting in the wings, more magnificent and bizarre than we could have dreamed. It expands our imagination about what is possible, forcing us to consider life not under a single, gentle sun, but under 10, in a world of shifting shadows and eternal, kaleidoscopic daylight. The study of these extreme environments is more than just cataloging facts. It is a fundamental exploration of physics, chemistry, and biology under conditions we are only beginning to comprehend. It reminds us that the night sky, for all its apparent tranquility, is a theater of constant dramatic change, a place where stars are born, live, and die in spectacular fashion, bound together in families of incredible complexity. The universe is vast, strange, and filled with wonders beyond our current imagination. The story of Decuple star systems is just one chapter in an epic that is still being written. Now we want to hear from you. What cosmic mystery captivates you the most? Is it the potential for life in these chaotic systems, the eerie synchronicity of the Christmas tree effect, or the ghostly presence of dark matter halos? Share your favorite piece of space weirdness in the comments below. Let's continue this conversation and explore the unknown together. If you enjoyed this journey to the limits of what's possible, make sure to subscribe and hit the bell so you don't miss our next adventure into the deepest, strangest corners of the cosmos. The universe is waiting.